Right now, at this very moment, the universe is accelerating, not just expanding, accelerating. Every second that passes, space itself stretches faster than the second before. The rate of this acceleration is staggering. Every day, the expansion velocity increases by roughly 1 million miles per hour. Think about that number. 1 million miles per hour. Every single day. This is not a metaphor. This is not speculation. This is measured physics, confirmed by multiple independent observations across decades of careful study. The universe is racing away from itself, and the force driving this acceleration remains one of the most profound mysteries in all of science. In 1998, two independent teams of astronomers made a discovery that would fundamentally change our understanding of the cosmos. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both studying distant supernova to measure how the universe's expansion had changed over cosmic time. They expected to find that gravity was gradually slowing the expansion, just as a ball thrown upward slows as Earth's gravity pulls it back. What they found instead was impossible. The distant supernova were dimmer than they should be. Not slightly dimmer, significantly dimmer. This meant they were farther away than standard cosmology predicted. The universe had not been slowing down as expected. It had been speeding up. The discovery rested on a specific type of stellar explosion called a type Ia supernova. These events occur when a white dwarf star accumulates matter from a companion star until it reaches a critical mass threshold of roughly 1.4 times the mass of our Sun. At this precise threshold, the white dwarf undergoes catastrophic thermonuclear fusion, exploding with a brightness so consistent that astronomers can use these explosions as standardized candles to measure cosmic distances. The physics behind this consistency is well understood. The explosion always involves the same mass, the same composition, the same nuclear reactions. This means that if you observe a type Ia supernova and measure how bright it appears from Earth, you can calculate exactly how far away it must be. Any deviation from the expected brightness reveals something fundamental about the geometry and expansion history of space itself. The teams observed dozens of these supernovae in distant galaxies, some so far away that their light had been traveling toward Earth for over 7 billion years. They measured the light carefully, determined the distances, and compared those distances to what Einstein's equations of general relativity predicted for a universe whose expansion was gradually slowing under the pull of its own gravity. The numbers were wrong. Every distant supernova appeared fainter than it should. This could only mean one thing. The fabric of space between us and those ancient explosions had stretched more than Einstein's equations alone could account for. Something was accelerating the expansion, something that was not matter, something that was not radiation, something entirely new. The statistical significance of the discovery was overwhelming. In science, researchers use a measure called sigma to quantify how unlikely a result is to occur by random chance. A 3 sigma result means there is roughly a 1 in 370 chance the observation is a statistical fluke. A 5 sigma result, the gold standard for discovery in physics, means the odds are about 1 in 3.5 million. The supernova measurements reached beyond 5 sigma. Multiple independent teams using different telescopes and different analysis methods all found the same result. The universe is accelerating. This was not error. This was not bias. This was reality. The astronomers named the mysterious force driving this acceleration dark energy. The name reflects our profound ignorance about its nature. Dark does not mean it blocks light. It means we cannot see it directly. We can only observe its gravitational effects on the expansion of space. Energy refers to the fact that, whatever this phenomenon is, it behaves like a smooth energy field permeating all of space, rather than clumping into structures like matter does. Dark energy does not form galaxies or stars or planets. It simply exists everywhere, pushing outward, causing space itself to expand at an ever-increasing rate. The amount of dark energy required to produce the observed acceleration is staggering. Careful measurements of the cosmic microwave background radiation, the ancient light from the early universe, combined with observations of galaxy clustering and supernova distances, all point to the same conclusion. Dark energy makes up roughly 68% of the total energy content of the universe. Everything else, all the stars, all the planets, all the gas clouds, all the black holes, all the ordinary matter we can see and touch, accounts for less than 5%. The remaining 27% is dark matter, another mysterious substance that we detect only through its gravitational effects. This means that more than 95% of the universe consists of phenomena we do not understand. We live in a cosmos dominated by the unknown. Here is where it gets deeply uncomfortable. The nature of dark energy challenges our most fundamental theories about how reality works. The simplest explanation is that dark energy represents the energy of empty space itself. Quantum field theory, the framework that describes the behavior of fundamental particles and forces, predicts that even empty vacuum is not truly empty. Virtual particles constantly pop into and out of existence, borrowing energy from the quantum foam for impossibly brief instants. This quantum activity gives the vacuum an intrinsic energy density. Einstein's equations of general relativity show that such an energy density would produce exactly the kind of repulsive gravitational effect we observe. The problem is the magnitude. When physicists calculate how much vacuum energy quantum field theory predicts, they get a number that is roughly 10 to the power of 120 times larger than the dark energy density we actually measure. This is not a small discrepancy. This is the worst prediction in the history of physics. Either quantum field theory is catastrophically wrong, or some unknown mechanism is cancelling out almost all of the vacuum energy, leaving behind just the tiny residual we observe. We have no idea which possibility is correct. The implications extend far beyond academic physics. Dark energy determines the ultimate fate of everything. If dark energy remains constant over cosmic time, as current measurements suggest, then the universe will continue expanding forever, accelerating without limit. Galaxies outside our local gravitational neighborhood will eventually recede so fast that their light can never reach us. The observable universe will shrink. In roughly 100 billion years, galaxies beyond our local group will disappear beyond a cosmic horizon, forever unreachable. In 1 trillion years, the night sky will be dark except for the stars in our own merged galaxy. In 10 to the power of 100 years, even those stars will burn out. The universe will become cold, dark, and empty, with matter spreading so thin that nothing interesting can ever happen again. This is not speculation. This is the mathematical consequence of continued accelerated expansion. Dark energy is not just ripping the universe apart, it is condemning it to an eternity of lonely isolation. But there is another possibility, far more terrifying. What if dark energy is not constant? What if it is growing stronger over time? This scenario, called phantom energy or Big Rip cosmology, leads to a fundamentally different end. If the repulsive force of dark energy increases, it will eventually overcome not just the gravity holding galaxy clusters together, but the gravity holding galaxies together, then solar systems, then planets, then molecules, then atoms themselves. In this scenario, the universe has a finite lifespan. Calculations suggest that if dark energy is growing stronger at certain rates, the universe could end in as little as 20 billion years. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems. In the final moments, roughly 1 month before the end, the solar system would disintegrate. 30 minutes before the end, Earth would explode. A fraction of a second before the end, atoms themselves would be ripped apart. Space would tear faster than the speed of light, severing every connection, destroying every structure until nothing remained but isolated fundamental particles in an infinitely stretched void. This is what accelerating expansion could mean if we have misunderstood dark energy's evolution. Before you drift off, leave a comment. What time is it where you are right now, and where in the world are you watching from? Current observations favor the simpler scenario where dark energy remains constant, but the uncertainties are still large enough that we cannot rule out the more exotic possibilities. Multiple space missions and ground-based surveys are working to measure dark energy's properties with greater precision. The Dark Energy Survey, operating from Chile, has mapped hundreds of millions of galaxies to trace how dark energy has affected cosmic structure over billions of years. The Dark Energy Spectroscopic Instrument, mounted on a telescope in Arizona, is measuring the distances to tens of millions of galaxies and quasars to create the most detailed three-dimensional map of the universe ever made. The European Space Agency's Euclid mission, launched in 2023, is observing billions of galaxies from orbit to measure how dark energy has influenced the distribution of matter across cosmic history. NASA is planning a successor mission called the Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, which will survey the sky with unprecedented sensitivity to measure dark energy's effects with even greater accuracy. These missions aim to answer a question that goes to the heart of physical law. Is dark energy truly constant, or does it evolve? The distinction matters because it reveals whether dark energy is Einstein's cosmological constant, a fixed property of space itself, or something more dynamic, a field that changes over time like the fields that govern electromagnetism and nuclear forces. If dark energy is constant, it suggests that space has an intrinsic energy that has been present since the beginning of time. If dark energy evolves, it suggests the existence of a new fundamental field pervading the cosmos, one that could interact with matter and radiation in ways we have not yet discovered. Either answer revolutionizes physics. Either answer demands explanations that our current theories cannot provide. The acceleration is real, the measurements are precise, the consequences are profound. Every day, space stretches faster. Every day, distant galaxies recede more quickly. Every day, the universe grows larger and more diffuse, driven by a force we can measure but cannot explain. Dark energy is not a minor correction to cosmology. It is the dominant component of reality, shaping the past, present, and future of everything that exists. Understanding what it is, why it has the strength it does, and whether it remains constant or changes over time represents one of the deepest challenges facing science. The universe is accelerating away from itself, and we are racing to understand why before the expansion carries the answers beyond our reach. This mystery connects to questions that have haunted humanity since we first looked up at the night sky and wondered about our place in the vastness. The mechanisms driving this acceleration reach back to the earliest moments after the Big Bang, forward to the ultimate fate of all structure, and inward to the quantum nature of space itself. The mechanism behind dark energy operates at the most fundamental level of physical reality, in the structure of space itself. To understand how something can push the universe apart requires understanding what space actually is. We tend to think of space as nothing, as the absence of matter, as the empty stage where cosmic events unfold. This is wrong. Space is a physical entity with measurable properties. It can bend, twist, ripple, and stretch. Einstein's general relativity revealed that massive objects curve space around them, and this curvature is what we experience as gravity. But space does more than respond to matter. Space itself can possess energy. This energy creates a pressure, and unlike the pressure of air in a balloon, which pushes outward in all directions, the pressure of space has a counterintuitive property. It is negative. Negative pressure sounds like an abstract mathematical trick, but it has concrete physical meaning. Normal, positive pressure, like the pressure inside a tire, pushes outward and causes expansion. If you release the air, the tire deflates. But negative pressure pulls inward, creating tension rather than compression. Here is where physics becomes strange. In Einstein's equations, pressure contributes to gravity. Positive pressure creates an attractive gravitational force. Negative pressure creates a repulsive gravitational force. The vacuum energy of empty space, if it exists, produces negative pressure exactly 3 times as strong as its positive energy density. This specific ratio, -3 to 1, appears directly from the mathematics of general relativity, combined with the requirement that the vacuum looks the same to all observers, regardless of their motion. The result is that vacuum energy gravitationally repels rather than attracts. It pushes space apart. Think of it this way. Imagine a rubber sheet stretched tight. Now imagine that the rubber itself is elastic and wants to expand. The more you stretch it, the more internal tension it develops, and this tension makes it want to stretch even more. This is roughly how dark energy behaves. As the universe expands and space stretches, more space comes into existence. Each new cubic meter of space contains the same dark energy density as every other cubic meter. So as the volume of space increases, the total amount of dark energy increases. More dark energy means stronger repulsion. Stronger repulsion means faster expansion. Faster expansion creates more space. This creates a runaway feedback process. The expansion accelerates without limit. This is not like a bomb exploding, where the initial energy is used up and the expansion eventually slows. This is self-sustaining. The energy source grows as space grows. The quantum field theory perspective offers another way to understand this mechanism, though it leads to profound puzzles. According to quantum mechanics, the vacuum is not empty but seethes with activity. Virtual particle pairs constantly appear and vanish in accordance with the Heisenberg uncertainty principle, which allows energy to be borrowed from nothing, provided it is returned within an impossibly short time interval. An electron and positron can pop into existence from pure vacuum, exist for roughly 10 to the -21 seconds, then annihilate back into nothingness. These fluctuations occur for all particle types, at all energy scales throughout all of space. Each fluctuation contributes a tiny amount of energy to the vacuum. When you add up all possible fluctuations across all possible energy scales, the total vacuum energy should be enormous. Quantum field theory suggests this energy should be real, should gravitate, and should dominate the dynamics of space-time. But here is the central mystery. The vacuum energy predicted by quantum field theory is so large that it should cause space to expand at a rate trillions upon trillions upon trillions of times faster than we observe. The universe should have blown itself apart in a fraction of a second after the Big Bang. Matter, radiation, structure, none of it would have had time to form. we would not exist to ask these questions. Yet we do exist. The universe is roughly 14 billion years old. Structure formed, galaxies condensed, stars ignited, life emerged. This requires that the actual vacuum energy is nearly zero, differing from the theoretical prediction by a factor of 10 to the power of 120. This is called the cosmological constant problem. It is the worst failure of prediction in physics. Either quantum field theory catastrophically overcounts the vacuum energy, or some unknown symmetry or mechanism cancels almost all of it, leaving only the tiny residual we observe as dark energy. No one knows which is correct. No one has a convincing explanation. The measurable effects of dark energy become apparent only across vast distances and cosmic timescales. On scales smaller than a few 100 million light-years, gravity overwhelms the repulsive effects of dark energy. Galaxy clusters remain bound. Galaxies hold together. Solar systems orbit stably. Atoms do not fly apart. Dark energy becomes important only when we examine how space itself behaves across billions of light-years. At these scales, the cumulative effect of dark energy's negative pressure becomes dominant. The expansion of space accelerates. Distant galaxies recede faster than they would in a universe containing only matter and radiation. The light from these galaxies gets stretched to redder wavelengths as space expands during the light's journey to Earth. By measuring this redshift and comparing it to the galaxy's distance, astronomers can determine the expansion rate as a function of cosmic time. This is how we know the expansion is accelerating. The detection methods rely on precise distance measurements to objects billions of light-years away. Type Ia supernovae provide one method, as discussed earlier. Their consistent peak brightness allows astronomers to determine distances by measuring how bright they appear. But there are other methods. Baryon acoustic oscillations provide an independent distance ruler imprinted in the distribution of galaxies. In the first few 100,000 years after the Big Bang, pressure waves rippled through the hot plasma filling the universe. These waves traveled at a fixed speed determined by the balance between radiation pressure and gravity. When the universe cooled enough for atoms to form, the pressure waves froze into place, leaving a characteristic scale imprinted in the cosmic microwave background radiation and in the clustering pattern of galaxies. This scale is roughly 500 million light-years. By measuring how large this scale appears at different distances and cosmic times, astronomers can trace the expansion history and detect the effects of dark energy. Gravitational lensing offers yet another method. Massive galaxy clusters bend space around them, distorting the light from background galaxies into arcs and multiple images. The degree of distortion depends on the geometry of space between us and the lensed galaxies. This geometry is affected by dark energy. By studying thousands of lensing systems and measuring how their properties change with distance, cosmologists can infer how dark energy has influenced the universe's expansion over billions of years. The growth rate of cosmic structure provides additional evidence. In a universe dominated by matter, gravitational clumping causes structure to grow at a predictable rate. Dark energy opposes this growth by accelerating the expansion and reducing the effectiveness of gravity. By measuring how the clustering of galaxies has evolved from the distant past to the present, astronomers can determine how much dark energy has been present at different epochs. All these independent methods agree. The universe began decelerating under the pull of its own matter. Then, roughly 5 billion years ago, the expansion began to accelerate as dark energy's repulsive effect became dominant. The transition from deceleration to acceleration occurred at a specific moment in cosmic history, when the density of matter had thinned enough that dark energy's contribution to the universe's total energy became comparable to matter's contribution. Before this transition, matter dominated and gravity slowed the expansion. After this transition, dark energy dominated and the expansion accelerated. We live in the era of acceleration. We live at a time when the universe is beginning its final, endless flight into diffuse oblivion. The physical picture that emerges is one of competing forces operating across cosmic scales. Gravity tries to pull matter together, to form structure to resist the expansion. Dark energy tries to tear space apart, to accelerate the expansion, to smooth out structure. On small scales, gravity wins. Planets orbit stars. Stars orbit galactic centers. Galaxies merge when they encounter each other. But on the larger scales, dark energy wins. The space between galaxy clusters expands faster than gravity can pull them together. The cosmic web of structure grows more diffuse. The universe as a whole accelerates into an ever more rapid expansion. We exist in the brief cosmic moment when both forces are comparable in strength, when structure still grows but acceleration has begun. This balance will not last. As the universe continues to expand, matter spreads thinner, while dark energy maintains constant density. The ratio of dark energy to matter increases relentlessly. Dark energy's dominance grows stronger with each passing billion years. Eventually, dark energy will be so overwhelmingly dominant that its repulsive effect will halt all structure formation. No new galaxies will condense from the expanding void. No new stars will form in regions where gas has been dispersed. The universe will transition from an era of ongoing creation to an era of inexorable decay. The last stars will form within the next few trillion years. After that, the cosmos will slowly darken as existing stars burn out, one by one, never to be replaced. This is the future dark energy has written into the fabric of reality. Understanding why dark energy has the precise strength it does, and not some vastly different value, remains one of the deepest problems in theoretical physics. The fact that dark energy is non-zero but incredibly tiny compared to theoretical predictions suggests that something fundamental is missing from our understanding. Some physicists propose that dark energy is not constant, but is a dynamical field, similar to the Higgs field that gives particles mass, or the inflaton field that drove cosmic inflation in the first fraction of a second after the Big Bang. In this picture, dark energy slowly evolves, changing its density and equation of state as the universe ages. Other physicists suggest that our very perception of acceleration might be wrong, that what we interpret as dark energy could actually be a sign that Einstein's general relativity breaks down on cosmological scales and needs modification. Still others propose that we live in a multiverse, where different regions have different values of dark energy, and we inevitably find ourselves in a region where dark energy is small enough to allow structure formation and life, simply because we could not exist anywhere else. Each explanation has profound implications. Each remains unproven. The search for answers drives some of the most ambitious observational programs in astronomy. Ground-based telescopes in Chile, Hawaii, and the Canary Islands scan the sky nightly, measuring the properties of millions of galaxies. Space-based observatories orbit above Earth's atmosphere, capturing light that would otherwise be absorbed or distorted. Powerful computers simulate the evolution of the universe, testing whether theoretical models match observed reality. Particle physicists search for new particles and forces that might explain dark energy's origin. Theoretical physicists develop new mathematical frameworks that might resolve the cosmological constant problem. The effort spans disciplines, institutions, and nations united by the recognition that understanding dark energy is essential to understanding existence itself. This quest began not with modern technology but with early 20th century observations that revealed the universe itself had a history, that it evolved from a denser, hotter past toward a more diffuse future. The first hint that the universe was not static came in 1912, when American astronomer Vesto Slipher, working at L in Arizona, measured the spectra of spiral nebulae and found something unexpected. The light from most of these objects was shifted toward the red end of the spectrum, indicating they were moving away from Earth at tremendous speeds. By 1925, Slipher had measured 45 nebulae and found that 40 were redshifted, some moving at velocities exceeding 1,000 kilometers per second. These were not small motions. These were cosmic velocities that suggested the nebulae were rushing away through space. But no one yet understood what the nebulae were or what their motion meant. The prevailing view held that the universe was eternal and unchanging, an infinite static cosmos that had always existed and would always exist in essentially the same form. Edwin Hubble changed everything in 1929. Working at the Mount Wilson Observatory in California with the 100-inch Hooker telescope, then the largest in the world, Hubble measured distances to these spiral nebulae using Cepheid variable stars as distance indicators. Cepheids are stars that brighten and dim in a regular pattern, and the period of their pulsation is directly related to their intrinsic brightness. By measuring a Cepheid's pulsation period, astronomers can determine how bright it actually is, and by comparing that to how bright it appears from Earth, they can calculate its distance. Hubble found that the spiral nebulae were galaxies, vast collections of billions of stars located far beyond the Milky Way. More importantly, he discovered a relationship between a galaxy's distance and its redshift velocity. The farther away a galaxy was, the faster it was receding. This relationship, now called Hubble's law, revealed that the universe itself was expanding. Space was stretching, carrying galaxies apart like dots on an inflating balloon. The implications were profound and immediate. If the universe was expanding now, it must have been smaller in the past. Following the expansion backward in time led to an inevitable conclusion. The universe had a beginning. Roughly 14 billion years ago, all of space and all the matter and energy within it emerged from an incredibly hot, incredibly dense state. This initial moment became known as the Big Bang, though the term was originally coined by physicist Fred Hoyle in 1949 as a derisive nickname for a theory he opposed. Hoyle favored the steady-state model, which proposed that the universe had always existed in roughly its current form, with new matter continuously created to fill the gaps left by expansion. But evidence accumulated against the steady-state model throughout the 20th century. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, provided decisive confirmation that the universe had indeed emerged from a hot, dense state. The radiation they detected was the cooled remnant of the intense heat from the early universe, now stretched by cosmic expansion into microwaves filling all of space. For decades after Hubble's discovery, astronomers worked to measure the expansion rate more precisely. This rate became known as the Hubble constant, usually denoted h0, and it quantifies how fast space expands per unit distance. The measurement proved extraordinarily difficult. Distance measurements to galaxies carried large uncertainties. Different methods gave different results. By the 1980s, estimates for the Hubble constant ranged from 50 to 100 kilometers per second per megaparsec, meaning that for every megaparsec of distance, roughly 3.3 million light-years, space expands by 50 to 100 kilometers per second. This factor of 2 uncertainty translated into huge uncertainties about the universe's age, its size, and its fate. Resolving this became a major goal of observational cosmology. The Hubble Space Telescope, launched in 1990 by NASA aboard the Space Shuttle Discovery, revolutionized distance measurements. Named for Edwin Hubble, the telescope orbited above Earth's atmosphere, avoiding the blurring and distortion that limits ground-based observations. In 1994, after corrective optics were installed to fix a flaw in its primary mirror, the Hubble Space Telescope began a systematic program to measure Cepheid variables in distant galaxies. The Hubble Space Telescope Key Project, led by astronomer Wendy Friedman, observed Cepheids in 31 galaxies and used them to calibrate other distance indicators that could reach even farther into space. By 2001, the project had determined the Hubble constant to be 72 kilometers per second per megaparsec, with an uncertainty of only 10%. This was a triumph of precision measurement. But measuring the expansion rate today tells only part of the story. To understand the universe's fate, astronomers needed to know how the expansion rate had changed over cosmic history. In a universe containing only matter and radiation, gravity would steadily slow the expansion. The deceleration rate would depend on how much matter the universe contained. If the matter density was high enough, gravity would eventually halt the expansion and pull everything back together in a big crunch. If the matter density was too low, the universe would expand forever, gradually slowing but never quite stopping. The critical boundary between these fates became a central question in cosmology throughout the late 20th century. This is where type Ia supernovae entered the story. The key insight developed in the 1980s and refined in the early 1990s was that these stellar explosions could serve as standardized candles visible across billions of light-years. Unlike Cepheids, which could only be detected in relatively nearby galaxies, supernovae were bright enough to be seen halfway across the observable universe. By measuring their peak brightness and comparing it to their redshift, astronomers could determine how the expansion rate had changed over cosmic time. If the expansion was slowing, distant supernovae would appear brighter than expected because space would have expanded less during their light's journey to Earth. If the expansion was accelerating, they would appear dimmer. The Supernova Cosmology Project began systematic searches for distant supernova in 1992, using wide-field cameras on ground-based telescopes to scan the same patches of sky repeatedly, looking for new points of light that suddenly appeared. The High-Z Supernova Search Team started similar observations in 1994. Both teams developed sophisticated pipelines to discover supernova, confirm their type through spectroscopy, measure their brightnesses as they rose to maximum light and then faded, and calculate their distances. The work required coordination between multiple observatories, careful calibration of instruments, and painstaking analysis of the data. Systematic uncertainties plagued every step. Dust in the host galaxies could dim the supernova. Intrinsic variations in supernova properties could introduce errors. Selection effects could bias the sample. By 1998, both teams had collected enough data to draw conclusions. The Supernova Cosmology Project published results based on 42 distant supernova. The High-Z team published results based on 16. Both found the same shocking result. The distant supernova were dimmer than expected. The universe was not decelerating, it was accelerating. The papers appeared in 1998 and 1999, and the scientific community reacted with a mixture of excitement and skepticism. The result seemed impossible. Nothing in theoretical physics predicted that the expansion should speed up. Acceleration required something new, some form of energy that created repulsive gravity, something that had not been included in cosmological models. Confirmation came quickly from multiple independent sources. The Wilkinson Microwave Anisotropy Probe, launched by NASA in 2001, measured the cosmic microwave background with unprecedented precision. The patterns of hot and cold spots in this ancient radiation encode information about the universe's composition and geometry. Analysis of the data revealed that ordinary matter and dark matter together accounted for only about 32% of the universe's total energy density. Something else, something that did not clump into structures, made up the remaining 68%. This something had to be dark energy. The probe's measurements precisely matched the supernova results. The 2-degree field galaxy redshift survey conducted between 1997 and 2003 using the Anglo-Australian telescope in New South Wales mapped the positions and distances of over 200,000 galaxies. The 3-dimensional map revealed the large-scale structure of the universe, showing how galaxies clustered into filaments and sheets separated by vast voids. The statistical properties of this structure depended on dark energy. Too much dark energy would have prevented structure from forming. Too little would have allowed more clumping than observed. The measured clustering pattern confirmed that dark energy made up roughly 70% of the universe's energy content, consistent with the supernova and cosmic microwave background measurements. The Sloan Digital Sky Survey, which began observations in 2000 from Apache Point Observatory in New Mexico, extended these measurements to even larger scales. Using a dedicated 2.5-meter telescope equipped with sophisticated imaging and spectroscopic instruments, the survey eventually mapped over 1 million galaxies across more than a third of the sky. The resulting 3-dimensional map traced structure back to times when the universe was less than half its current age. Analysis of this structure confirmed that dark energy had been relatively constant over the past several billion years, maintaining roughly the same density even as matter spread thinner. The Planck satellite, launched by the European Space Agency in 2009, provided the most detailed measurements yet of the cosmic microwave background. Operating from a position 1.5 million kilometers from Earth, beyond the Moon's orbit, Planck mapped the entire sky in 9 frequency bands with extraordinary sensitivity. The mission concluded in 2013 after 4 years of observations. Analysis of the data, published in detailed papers over the following years, determined the universe's composition to within 1% accuracy. Dark energy accounts for 68.3% of the total energy density. Dark matter accounts for 26.8%. Ordinary matter accounts for 4.9%. These measurements agreed with supernova and galaxy clustering studies, providing independent confirmation from the early universe that dark energy dominates cosmic evolution. Ground-based surveys continued to refine dark energy measurements throughout the 2010s. The Dark Energy Survey, operating from the 4-meter Victor M. Blanco telescope at Cerro Tololo Inter-American Observatory in Chile, began observations in 2013 and ran through 2019. The survey imaged over 300 million galaxies across 5,000 square degrees of the southern sky, roughly 1/8 of the entire celestial sphere. By measuring how dark energy affected the growth of cosmic structure, the bending of light by gravity, the clustering of galaxies, and the properties of supernovae, the survey provided multiple independent measurements that all pointed to the same conclusion. Dark energy behaves like Einstein's cosmological constant, maintaining essentially constant density as the universe expands. The evolution from Hubble's initial discovery to modern precision cosmology spans barely a century, yet it has revolutionized our understanding of existence. In 1929, we learned the universe was expanding. In 1965, we confirmed it had a beginning. In 1998, we discovered the expansion was accelerating. Each revelation overturned previous assumptions and opened new mysteries. The technological progression made these discoveries possible. Early photographic plates and visual observations gave way to electronic detectors millions of times more sensitive. Single observations by individual astronomers gave way to systematic surveys mapping billions of objects. Ground-based telescopes were complemented by space missions that observed wavelengths impossible to detect from Earth's surface. Computational power increased by factors of billions, allowing simulations that modeled the universe's evolution in exquisite detail. Yet despite this progress, the fundamental nature of dark energy remains as mysterious today as it was when first discovered. We have measured its effects with remarkable precision. We know its density, its equation of state, its impact on cosmic evolution. But we do not know what it is. We do not know why it has the strength it does. We do not know whether it will remain constant or change in ways that alter the universe's ultimate fate. These questions drive current observations and theoretical research, connecting the larger scales of cosmic structure to the smallest scales of quantum physics in ways that challenge our deepest understanding of physical law. The measurements revealing dark energy's properties also expose our peculiar position within the cosmos, living at a moment when acceleration has recently begun, but structure still persists. The timing of dark energy's dominance raises questions that probe the foundations of cosmology. We exist at an epoch when dark energy has just begun to dominate the universe's expansion, yet structure formation has not completely ceased. This seems like an extraordinary coincidence. For the first 9 billion years of cosmic history, matter dominated and gravity shaped the evolution of structure. Galaxy clusters formed. The cosmic web of filaments and voids emerged. Stars ignited within condensing gas clouds. Then, roughly 5 billion years ago, as matter thinned and dark energy maintained constant density, the balance tipped. Acceleration began. We live mere billions of years after this transition. On cosmic timescales measured in trillions of years, our existence clusters suspiciously close to the moment when the universe fundamentally changed its behavior. This temporal coincidence becomes even more striking when you consider the vastness of cosmic time. The universe has existed for roughly 14 billion years. It will continue expanding for what may be an infinite future. If intelligent observers could arise at any point in this history, why do we find ourselves living so close to the transition from deceleration to acceleration? In the far future, perhaps 100 billion years from now, observers would see a universe utterly dominated by dark energy, with acceleration having shaped cosmic evolution for most of its history. In the distant past, say 1 billion years after the Big Bang, observers would have seen a universe dominated by matter and radiation, with no hint that acceleration would someday begin. But we exist right at the boundary, when both matter and dark energy contribute comparable amounts to the universe's total energy budget. This is known as the coincidence problem, and it has no satisfactory explanation within standard cosmology. Some physicists argue this timing is not coincidence, but anthropic necessity. Complex structures like galaxies, stars, and planets require matter to dominate for long enough that gravity can overcome expansion and pull material together. If dark energy had dominated earlier, before galaxies could form, no stars would have ignited, no heavy elements would have been forged in stellar cores, no planets could have condensed from enriched gas clouds, and no life could have emerged. Conversely, intelligent life requires billions of years to evolve. Stars must form, live out their lives, explode as supernovae, enrich the interstellar medium with carbon, oxygen, nitrogen, and other elements essential for chemistry and biology. Second and third generation stars must form from this enriched material. Planets must cool, atmospheres must develop, single-celled organisms must evolve into complex multicellular life. All this takes time, perhaps several billion years at minimum. By the time intelligence emerges, dark energy has naturally begun to dominate, simply because enough time has passed for matter to thin sufficiently. In this view, we necessarily observe the coincidence because only at this epoch could observers exist. This anthropic argument remains controversial. Many physicists find it unsatisfying because it does not explain why dark energy has the specific value it does, only why we observe it at a particular cosmic time. The argument also depends on assumptions about what conditions are necessary for life, and we have only one example to draw from. Perhaps life could arise under radically different conditions we have not imagined. Perhaps intelligence could emerge in a universe dominated by dark energy, forming from structures that do not require galaxies or stars. Until we understand life's full range of possibilities, anthropic arguments remain speculative. The broader context of dark energy connects to cosmic inflation, the brief period of exponentially rapid expansion that occurred in the first fraction of a second after the Big Bang. Inflation and dark energy both involve accelerated expansion driven by something with negative pressure. During inflation, this acceleration was incredibly violent, increasing the universe's size by a factor of at least 10 to the power of 26 in roughly 10 to the negative 32 seconds. The energy density driving inflation was enormous, perhaps 10 to the power of 80 times greater than dark energy's current density. After inflation ended, this energy decayed into the hot bath of particles and radiation that became the observable universe. Dark energy, in contrast, appears stable. It does not decay. It does not dilute as space expands. It simply maintains constant density, driving gentle acceleration that will continue forever. The connection between inflation and dark energy remains mysterious. Both phenomena involve scalar fields, fields that have a value at every point in space, but no direction. The Higgs field is another example of a scalar field, giving mass to fundamental particles through its interactions. During inflation, the inflaton scalar field rolled slowly down a potential energy curve, its energy dominating the universe and driving expansion. When the field reached the bottom of the potential, inflation ended and the field's energy converted into particles. Dark energy might be another scalar field, often called quintessence, rolling extremely slowly down an extremely flat potential. Or dark energy might be Einstein's cosmological constant, a fixed property of space-time itself rather than a dynamical field. Current observations cannot distinguish between these possibilities. Both predict essentially the same behavior on observable timescales. The measurement challenges in studying dark energy stem from the need to observe effects that become significant only across billions of light-years and billions of years of cosmic history. No single measurement technique provides definitive answers. Each method has systematic uncertainties and potential biases. Supernova observations require careful corrections for dust extinction, intrinsic brightness variations, and evolution in supernova properties over cosmic time. Cosmic microwave background measurements depend on complex models of how matter and radiation behaved in the early universe. Galaxy clustering measurements require sophisticated simulations to understand how dark matter, baryonic matter, and dark energy interact to produce observed structures. Gravitational lensing measurements depend on accurate models of how mass is distributed within galaxy clusters. only by combining multiple independent techniques can cosmologists be confident in their conclusions. Secondary effects of dark energy appear in subtle ways throughout cosmic structure. The integrated Sachs-Wolf effect describes how light from the cosmic microwave background gains or loses energy as it passes through gravitational potentials that are growing or decaying. In a matter-dominated universe, potentials remain essentially constant as structure grows. But in a dark energy-dominated universe, potentials decay because dark energy opposes the gravitational growth of structure. Photons passing through decaying potentials gain a net energy boost, making the cosmic microwave background slightly hotter, in directions where large voids or superclusters lie between us and the surface of last scattering. This effect was predicted in the 1960s but only observed in the early 2000s when both cosmic microwave background maps and galaxy surveys became detailed enough to correlate. The detection provided independent confirmation that dark energy was suppressing the growth of cosmic structure. The growth rate of structure provides another window into dark energy's effects. In a universe containing only matter, denser regions grow denser over time as gravity pulls more material into them. The growth rate depends on the matter density and the expansion rate. But dark energy changes this relationship. By accelerating the expansion, dark energy reduces how effectively gravity can pull matter together. Structure grows more slowly than it would in a matter-only universe. By measuring how fast structure is growing at different times, through observations of galaxy clustering and weak gravitational lensing, cosmologists can test whether dark energy behaves as expected or shows hints of being something more exotic than a cosmological constant. Our position within the universe affects what we can measure about dark energy in subtle but important ways. We sit inside a galaxy within a small cluster of galaxies called the local group. The local group contains the Milky Way, Andromeda, Triangulum, and about 50 smaller dwarf galaxies, all bound together by their mutual gravity. This bound system will not participate in the accelerating expansion. Andromeda is actually approaching us at roughly 110 kilometers per second, and the two galaxies will collide and merge in about 4 billion years. The merged galaxy, sometimes called Milkomeda, will settle into a gravitationally bound system where dark energy's effects remain negligible. Only outside the local group, beyond distances of several million light-years, does the expansion of space become significant. Only there does dark energy's influence become measurable. This local perspective limits what we can directly observe. We cannot measure the expansion rate by watching nearby galaxies because they are not participating in the expansion. We must look beyond our cosmic neighborhood to galaxies tens or hundreds of millions of light-years away before expansion becomes the dominant motion. This means our measurements always involve looking back in time, because light from distant objects takes time to reach us. We see those galaxies not as they are now, but as they were when their light began its journey. A galaxy 1 billion light-years away appears, as it was 1 billion years ago. This light travel time effect turns every telescope into a time machine, allowing us to observe the universe's history. But it also means we never see the current state of distant regions. We only see their past. The Copernican principle, which holds that we do not occupy a special position in the universe, becomes testable through dark energy observations. If we lived at the center of a giant void, a region of space with lower than average density, local measurements of the expansion rate could differ from measurements to distant regions. The underdense region would expand faster than average, making nearby galaxies recede more quickly than they should. This could mimic the effects of dark energy. Some cosmologists have proposed that we might live in such a void, and what we interpret as cosmic acceleration is actually a local anomaly. However, Detailed measurements of the cosmic microwave background, galaxy distributions, and supernova distances all indicate that our local region has typical density. We do not appear to sit in a large void. The acceleration appears universal, the same in all directions and at all distances we can measure. This consistency supports the dark energy interpretation. The question of whether our cosmic environment is typical or special connects to deeper issues about cosmic variance. The observable universe is finite, limited by the speed of light and the finite age of the universe. We can only see roughly 93 billion light-years in any direction, the distance light could have traveled since the Big Bang, accounting for cosmic expansion. Beyond this horizon lies more universe, but its light has not had time to reach us. We have no direct information about conditions beyond the observable horizon. Statistical studies based on computer simulations suggest that the observable universe is large enough that cosmic variance, the random variation in properties from one region to another, should be small. Our measurements should reflect universal properties rather than local accidents. But we cannot be absolutely certain. The universe beyond our horizon could be radically different. Dark energy might vary from place to place in ways we cannot detect. These considerations underscore how our understanding of dark energy depends on observational cosmology, on measurements of light from distant sources that reveal cosmic history. Unlike laboratory physics, where experiments can be repeated under controlled conditions, cosmology offers only one universe to study. We cannot rerun cosmic evolution with different initial conditions. We cannot travel to distant regions to check whether our interpretations are correct. We can only observe, measure, analyze, and build models that try to make sense of what we see. The robustness of these models depends on having multiple independent lines of evidence that all point to consistent conclusions. When supernova observations, cosmic microwave background measurements, galaxy clustering studies, and gravitational lensing surveys all indicate the same dark energy properties, confidence grows that our interpretation reflects reality rather than systematic error or misunderstanding. Yet even with this convergence of evidence, fundamental tensions remain in our measurements, disagreements between different techniques that hint at either systematic problems or new physics waiting to be discovered. The most precise measurements of the universe's expansion rate do not agree. This is not a minor discrepancy. This is not measurement noise. This is a fundamental tension that has grown more severe as observations have become more accurate. Two different approaches to measuring the Hubble constant, the number that quantifies how fast space expands, give answers that differ by roughly 9%. In science, 9% might seem small, but when both measurements claim uncertainties of only 2 or 3%, and when they disagree at a statistical significance exceeding 5 sigma, the tension becomes impossible to dismiss as random error. Something is wrong. Either one or both measurement methods harbor unrecognized systematic errors, or our cosmological model is incomplete, missing some crucial ingredient that would reconcile the discrepancy. The first method builds what astronomers call the cosmic distance ladder. It begins with the most local, directly measurable distances and works outward step by step to greater cosmic scales. The foundation rests on parallax measurements to nearby stars. As Earth orbits the Sun, nearby stars appear to shift positions slightly against the background of more distant stars. This shift, called parallax, is inversely proportional to distance. Measure the parallax angle, and you know the distance. The European Space Agency's Gaia mission, launched in 2013, has measured parallaxes for over 1 billion stars with extraordinary precision, some accurate to within a few percent. These parallax distances anchor the entire cosmic distance scale. The next rung uses Cepheid variable stars. These pulsating stars exist in our galaxy and in nearby galaxies, close enough that parallax measurements calibrate their true brightness. Henrietta Leavitt discovered in 1912 that Cepheids with longer pulsation periods have higher intrinsic luminosities. This period luminosity relationship allows any Cepheid's true brightness to be determined by measuring how long it takes to complete one cycle of brightening and dimming. Once you know the true brightness and measure the apparent brightness, you can calculate the distance. The Hubble Space Telescope has observed Cepheids in galaxies out to distances of roughly 130 million light-years, far enough to measure how space expands at these intermediate scales. The final rung uses Type Ia supernovae. These stellar explosions are far brighter than Cepheids, bright enough to be seen across billions of light-years. But their peak brightness must be calibrated, and this calibration requires knowing the distances to nearby supernovae. This is where Cepheids become crucial. By measuring Cepheids in galaxies that have hosted Type Ia supernovae, astronomers determine those supernova distances directly, calibrating how bright Type Ia supernova truly are. With this calibration in hand, more distant supernova too far for Cepheid measurements reveal the expansion rate across cosmological distances. Each rung depends on the previous rung. Parallaxes calibrate Cepheids. Cepheids calibrate supernovae. Supernovae measure the Hubble constant. Adam Rees, one of the scientists who discovered accelerating expansion in 1998, has led the most precise implementation of this distance ladder approach. His team's measurements, published in papers throughout the 2010s and culminating in refined results in 2022, determine the Hubble constant to be 73.04 kilometers per second per megaparsec, with an uncertainty of only 1.04. This means that for every megaparsec of distance, space expands by 73 kilometers per second. The measurement precision is remarkable, better than 2% accuracy. The systematic uncertainties have been carefully examined. The team has checked for potential biases in Cepheid measurements, supernova properties, dust extinction, metallicity effects, and selection criteria. Every conceivable source of error has been scrutinized. The result remains robust. The second method takes an entirely different approach. Instead of building outward from local measurements, it looks back to the earliest light in the universe, the cosmic microwave background radiation. This ancient light was emitted roughly 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form and photons could travel freely through space. The temperature fluctuations in this radiation, tiny variations of only 1 part in 100,000, contain a wealth of information about the universe's properties at that early time. The pattern of hot and cold spots depends on how matter and radiation were distributed, how they interacted, and how space was curved. Detailed measurements of this pattern, particularly the characteristic angular scale of the fluctuations, allow cosmologists to determine all the fundamental parameters of the universe, including the Hubble constant. The Planck satellite provided the most precise measurements of the cosmic microwave background. Operating for 4 years and mapping the entire sky multiple times in 9 frequency bands, Planck measured the temperature fluctuations with unprecedented accuracy. Analysis of this data, combined with theoretical models of how the early universe evolved, determines the Hubble constant to be 67.4 kilometers per second per megaparsec, with an uncertainty of roughly 0.5%. This measurement assumes the standard cosmological model is correct, that the universe contains dark matter, dark energy behaving as a cosmological constant, ordinary matter, and radiation, all evolving according to Einstein's general relativity. Given these assumptions, the cosmic microwave background data tightly constrains the Hubble constant. The disagreement between these two values is significant: 73.04 versus 67.4, a difference of roughly 5.6 kilometers per second per megaparsec. This might not sound like much, but relative to the measurement's precision, it represents a 9% discrepancy. The statistical significance exceeds 5 sigma, meaning the probability that this disagreement arose by chance is less than 1 in a million. Both measurements have been checked and rechecked. Both teams have looked for systematic errors. Both results have been confirmed by independent groups using similar methods. The Hubble Space Telescope distance ladder measurement agrees with results from other telescopes and other Cepheid samples. The Planck cosmic microwave background measurement agrees with earlier results from the Wilkinson microwave anisotropy probe. The tension is real. Why should these two methods agree? Because they are measuring the same universe. The Hubble constant is a fundamental property of cosmic expansion. It should have one true value. If the standard cosmological model is correct, then measurements from the early universe should predict the same expansion rate we observe locally. The cosmic microwave background tells us the conditions shortly after the Big Bang. The model tells us how those conditions evolved over 13.8 billion years to produce the universe we see today. The predicted local expansion rate should match what the distance ladder measures, but it does not. Either the model is missing something, or one of the measurement methods contains an unrecognized error. Dark energy enters this debate as a potential resolution. The standard model assumes dark energy behaves as Einstein's cosmological constant, maintaining exactly constant density as the universe expands. But what if dark energy is not constant? What if it has evolved over cosmic time, perhaps growing slightly stronger in recent epochs? Early dark energy, a theoretical modification where dark energy was present but weaker in the early universe, could alter the cosmic microwave background in subtle ways that would change the inferred Hubble constant. If dark energy was different in the past, the evolution from early conditions to current expansion would proceed differently than the standard model predicts. This could potentially reconcile the tension between early universe and late universe measurements. However, early dark energy faces challenges. The cosmic microwave background is extraordinarily well measured. Adding early dark energy to the model does not improve the fit to the data in most analyses. The tension between different cosmological measurements persists, even when early dark energy is included. Other proposed modifications, such as changes to neutrino properties, additional relativistic particles in the early universe, or modifications to gravity, have been explored with similar limited success. No single explanation has emerged that naturally resolves the Hubble tension, while remaining consistent with all other cosmological observations. The stakes extend beyond the Hubble constant itself. If the tension cannot be resolved through better measurements or identified systematics, it suggests our cosmological model is fundamentally incomplete. This would be profound. The standard model, called lambda cold dark matter, has successfully explained an enormous range of observations. It predicted the acoustic peaks in the cosmic microwave background before they were measured. It explained the large-scale structure of galaxy clustering. It accounted for the abundances of light elements forged in the Big Bang. It described how galaxies evolve and form stars. Finding that this model breaks down would overturn decades of theoretical understanding and observational confirmation. Some physicists argue the tension might not indicate new physics, but rather underestimated systematic errors in one or both measurement methods. Perhaps Cepheid calibrations are affected by crowding in dense stellar fields, making distance measurements systematically wrong. Perhaps dust extinction is not properly accounted for, dimming supernovae more than models predict. Perhaps the cosmic microwave background measurements are contaminated by foreground emissions from our galaxy. Perhaps the theoretical models used to interpret cosmic microwave background data oversimplify the physics of the early universe. Extensive studies have examined all these possibilities. So far, no smoking gun has emerged. The measurements appear robust. Other researchers propose that the tension reveals fundamental limitations in our ability to measure cosmic distances. Perhaps type Ia supernovae are not as standardizable as assumed. Perhaps their peak brightnesses depend on their environment or their progenitor systems in ways that have not been fully characterized. Perhaps Cepheid period luminosity relationships vary with metallicity, the abundance of elements heavier than hydrogen and helium, more than current models account for. These effects could introduce subtle biases that accumulate through the distance ladder, producing systematically wrong results. Testing these hypotheses requires enormous observational effort, measuring hundreds or thousands of Cepheids and supernovae to statistically quantify potential variations. The James Webb Space Telescope, launched in December 2021, offers new capabilities for addressing the Hubble tension. Its infrared sensitivity and unprecedented resolution allow it to observe Cepheids in more distant galaxies than ever before possible. Extending the distance ladder to greater depths. Initial observations in 2022 and 2023 by Adam Rees and collaborators used the James Webb Space Telescope to measure Cepheids in galaxies previously observed by the Hubble Space Telescope. The goal was to check whether Hubble's Cepheid measurements were biased by crowding or other systematic effects. The James Webb measurements confirmed the Hubble results. The distances were consistent. The Hubble constant remained near 73. The tension persisted. Future observations aim to provide independent measurements that do not rely on either the distance ladder or the cosmic microwave background. Gravitational wave detections from merging neutron stars or black holes carry information about distance encoded in the amplitude of the gravitational wave signal. If the merger also produces electromagnetic radiation that allows the host galaxy's redshift to be measured, the event becomes a standard siren, analogous to a standard candle, but using gravity waves instead of light. The Laser Interferometer Gravitational Wave Observatory detected such an event in August 2017, when two neutron stars merged in a galaxy 40 megaparsecs away. The measurement yielded a Hubble constant of 70, though with large uncertainties. As gravitational wave detectors become more sensitive and detect more events, this method will provide increasingly precise, independent measurements. Strong gravitational lensing offers another approach. When a massive galaxy lies directly along the line of sight to a distant quasar, the galaxy's gravity bends and magnifies the quasar's light, often producing multiple images. Light taking different paths around the lens travels different distances and arrives at different times. If the quasar's brightness varies, these variations appear in the multiple images with time delays that depend on the geometry and the Hubble constant. Measuring these time delays, combined with models of the lensing galaxy's mass distribution, yields an independent determination of the expansion rate. The HCEO-LICAO collaboration, measuring time delays for 6 lensed quasars, found a Hubble constant of 73.3, consistent with the distance ladder but in tension with cosmic microwave background measurements. The debate continues. Papers arguing for systematics appear alongside papers arguing for new physics. Conferences feature passionate discussions about measurement techniques and theoretical interpretations. The community has not reached consensus. This is science at its most dynamic, where observations challenge theory and force deeper understanding. The Hubble tension might be resolved through better measurements that identify a subtle systematic error. Or it might represent the first crack in the standard cosmological model, the first hint that dark energy is more complex than a simple cosmological constant, or that gravity behaves differently on cosmic scales than general relativity predicts, or that the early universe contained physics we have not yet discovered. What makes this tension particularly intriguing is that it involves the most fundamental measurements in cosmology. The expansion rate determines the universe's age, its size, its future evolution. Getting this number wrong means misunderstanding cosmic history. The tension forces humility. Despite extraordinary observational precision and sophisticated theoretical models, we do not fully understand how the universe expands. This ignorance connects to other mysteries, to questions about why dark energy exists, why it has the strength it does, and whether the simple picture of constant vacuum energy captures reality. The resolution might come from unexpected directions, from observations that probe dark energy's behavior in ways that seem initially unrelated to the Hubble tension, but reveal counterintuitive properties that reshape our understanding. Dark energy behaves in ways that violate every intuition we have developed about how energy and matter interact. Matter interact. Consider the most basic principle of thermodynamics. Energy is conserved. You cannot create or destroy it, only transform it from one form to another. The total energy in an isolated system remains constant. This principle has been tested in countless experiments across every domain of physics, from subatomic particles to galactic scales. It is fundamental, yet dark energy appears to violate this principle in the most spectacular way possible. As the universe expands and space stretches, more space comes into existence. Each new cubic meter of space contains the same dark energy density as every existing cubic meter. More space means more dark energy. The total amount of dark energy in the universe increases continuously, without limit, forever. Where does this energy come from? The answer challenges everything we think we understand about conservation laws. The resolution lies in understanding that energy conservation applies only in systems where time symmetry holds, where the laws of physics remain unchanged as time passes. In an expanding universe, time symmetry breaks. The universe today differs fundamentally from the universe yesterday or tomorrow. Space itself evolves. In general relativity, energy conservation is not a universal law, but a consequence of space-time symmetry. When space-time is dynamic and curved, global energy conservation becomes ill-defined. You can define energy locally within small regions, but adding up these local energies to get a total universal energy does not work in a meaningful way. The expansion of space means that energy can be created not from nothing, but from the geometry of space-time itself. Dark energy's increase is balanced by negative gravitational potential energy associated with the universe's expansion. The universe as a whole can create energy because it is not an isolated system in the traditional thermodynamic sense. This explanation is mathematically rigorous but conceptually bizarre. Think about what this means. Empty space is not empty. Every cubic centimeter of vacuum contains energy, not much energy. Current measurements indicate the dark energy density is roughly 6.9 times 10 to the negative 30 grams per cubic centimeter. This is extraordinarily small, equivalent to about 6 hydrogen atoms per cubic meter. But space is vast. Add up all the dark energy in the observable universe, and you get roughly 10 to the power of 70 joules, a number so large it defies intuitive comprehension. More remarkably, this energy has weight. Energy and mass are equivalent according to Einstein's famous equation E equals mc squared. Dark energy gravitates. But unlike ordinary mass, which creates attractive gravity pulling objects together, dark energy creates repulsive gravity, pushing space apart. The mechanism is the negative pressure discussed earlier, which produces a gravitational field 3 times stronger than the energy density alone would create, but with opposite sign. The result is net repulsion. Here is the truly backward aspect. Adding energy to a system normally heats it up, increases its kinetic energy, makes things move faster in random directions. But adding dark energy to the universe causes it to expand faster in an organized way. The expansion is not chaotic but smooth, carrying every point in space away from every other point at a rate proportional to their separation. This is not an explosion where material flies outward from a central point into surrounding empty space. This is the stretching of space itself, occurring uniformly everywhere. There is no center. There is no edge. Every location experiences the same expansion. An observer in any galaxy would see all other distant galaxies receding, with velocities proportional to distance, exactly as we observe from Earth. This cosmological principle, that the universe appears the same from any location, is deeply counterintuitive, but supported by all observations. Consider an analogy drawn from everyday experience, though no analogy captures the full strangeness. Imagine a balloon being inflated. Dots drawn on the balloon's surface represent galaxies. As the balloon expands, the dots move apart. Importantly, the dots themselves do not move through the rubber. The rubber stretches, carrying the dots with it. An ant sitting on one dot would see all other dots receding, with farther dots receding faster. This mimics cosmic expansion. But the analogy breaks down in crucial ways. The balloon expands into surrounding 3-dimensional space. The universe's expansion does not occur into anything. Space itself expands. There is no external dimension. The balloon has a center inside it. The universe has no center. The balloon's surface is 2-dimensional, curved into 3 dimensions. The universe appears to be 3-dimensional space that may or may not be curved into higher dimensions we cannot perceive. Despite these limitations, the balloon analogy helps visualize how expansion can be uniform, yet produce distance-dependent recession velocities. Observational evidence for dark energy's counterintuitive properties comes from multiple independent sources that paint a consistent picture. The most direct evidence remains the dimming of distant Type Ia supernovae, when astronomers plot supernova distance versus redshift. The relationship curves in a specific way that indicates acceleration. Supernovae at redshifts between 0.5 and 1.0, corresponding to light travel times of 5 to 8 billion years, appear systematically fainter than they would in a universe whose expansion was slowing. This dimming is not subtle. It amounts to roughly 25% less brightness than expected, corresponding to about 10% greater distance. The effect has been measured in hundreds of supernovae by multiple independent teams using different telescopes and different analysis methods. The conclusion is inescapable. Space has stretched more than it would have if expansion were decelerating. Acceleration began roughly 5 billion years ago and has continued to the present. The cosmic microwave background provides complementary evidence through its detailed temperature pattern. The hot and cold spots in this ancient radiation encode information about the universe's geometry, density, and composition when the light was emitted 380,000 years after the Big Bang. One crucial feature is the angular scale of the first acoustic peak, the characteristic size of the largest temperature fluctuations. This scale depends on the geometry of space. In a flat universe where parallel lines remain parallel forever and the angles of triangles sum to exactly 180 degrees, the first peak appears at an angular scale of roughly 1 degree. Planck measurements determined the peak location to within a fraction of a percent. The result indicates the universe is flat to within measurement precision. But achieving this flatness requires the total energy density to have a specific critical value. Measurements of matter density, both ordinary and dark, account for only about 32% of this critical density. Something else must make up the remaining 68%. That something is dark energy. Its existence is required to explain why space is flat. Galaxy clustering over cosmic time reveals dark energy's effect on structure growth. In a matter-dominated universe, denser regions grow denser as gravity pulls more material into them. The clustering strength increases predictably over time, but dark energy opposes this growth by accelerating the expansion and reducing gravity's effectiveness. By measuring galaxy clustering at different distances, corresponding to different times in cosmic history, astronomers can track how structure growth has been suppressed. The Sloan Digital Sky Survey and subsequent surveys measured clustering in samples containing millions of galaxies, spanning billions of years of look-back time. The measurements show that structure growth slowed noticeably over the past 5 billion years, exactly when dark energy began dominating. The effect is statistically significant and quantitatively matches theoretical predictions for a universe with dark energy making up 68% of the total energy budget. Computer simulations allow cosmologists to test whether their understanding of dark energy produces universes that match observations. These simulations start with initial conditions representing the universe shortly after the Big Bang, then evolve billions of particles forward through cosmic time using the laws of gravity and hydrodynamics. The simulations include dark matter, which gravitationally attracts and forms the scaffolding for structure. They include ordinary matter, which can cool, condense, and form stars. They include dark energy, which accelerates the expansion. Running these simulations on powerful supercomputers produces synthetic universes that can be compared to real observations. The Illustri's simulation, completed in 2014, evolved roughly 12 billion resolution elements from redshift 127 to the present, producing a cube of space roughly 106 million light-years on each side. The resulting galaxy distributions, including their masses, shapes, clustering patterns, and evolution, closely matched observations. Similar large simulations like Eagle, Illustris TNG, and Millennium Run have produced consistent results. The standard cosmological model, including dark energy as a cosmological constant, successfully reproduces the observed universe in exquisite detail. Yet the statistical improbability of dark energy's measured value haunts these successes. As mentioned earlier, quantum field theory predicts a vacuum energy density 10 to the power of 120 times larger than observed. This is not a minor discrepancy that could be explained by measurement, uncertainty, or theoretical approximation. This is a prediction that is wrong by 120 orders of magnitude. Imagine predicting that a journey will take 1 second and discovering it actually takes 10 to the power of 120 seconds. That time span exceeds the age of the universe by a factor of 10 to the power of 110. The prediction is not just wrong, it is catastrophically, incomprehensibly wrong. No other prediction in physics has ever been this far off. Either quantum field theory's calculation of vacuum energy is fundamentally flawed, Or some unknown mechanism cancels nearly all the vacuum energy, leaving only the tiny observed residual. Several theoretical frameworks attempt to resolve this cosmological constant problem. Supersymmetry, a proposed symmetry between matter particles and force-carrying particles, predicts that contributions to vacuum energy from bosons and fermions cancel almost exactly, leaving a much smaller net vacuum energy. But supersymmetry has not been observed at particle accelerators despite extensive searches. If it exists, it must be broken at energy scales we have not yet probed, and broken symmetry typically produces large vacuum energy corrections that bring back the original problem. String theory, which attempts to unify quantum mechanics and gravity by treating fundamental particles as tiny vibrating strings, predicts a landscape of possible vacuum states, perhaps 10 to the power of 500 different configurations, each with different vacuum energy. In this picture, we live in one particular vacuum with small positive dark energy, simply because vacua with larger dark energy do not allow structure formation and life. This anthropic explanation is philosophically troubling to many physicists because it seems to give up on predicting the vacuum energy from fundamental principles. Modified gravity theories offer a radically different approach. Perhaps the acceleration we observe is not caused by dark energy at all, but by a breakdown of general relativity on cosmic scales. Einstein's equations might require correction terms that become significant across billions of light years. These modifications could produce apparent acceleration without requiring dark energy. Numerous modified gravity theories have been proposed with names like FR gravity, scalar tensor theories, and massive gravity. Each modifies Einstein's equations in specific ways and makes predictions that can be tested observationally. So far, none has successfully explained all cosmological observations while remaining consistent with solar system tests of gravity and other constraints. General relativity continues to pass every test. The simplest explanation remains that general relativity is correct and dark energy exists. Observational tests increasingly constrain how dark energy can behave. The equation of state parameter, usually denoted W, quantifies the relationship between dark energy's pressure and density. For a cosmological constant, W equals exactly -1. For dynamical dark energy fields, W can differ from -1 and can change over time. Current measurements from multiple sources, including supernova, cosmic microwave background, and galaxy clustering, determine WW to be -1.03 plus or -0.03. This is consistent with a cosmological constant, but allows for small deviations. Future observations aim to measure W to within 1% accuracy and detect any evolution in W over cosmic time. Such measurements would reveal whether dark energy is truly constant or something more complex. The counterintuitive nature of dark energy extends to its long-term consequences. In a matter-dominated universe, structure would continue growing forever, albeit more slowly as matter spreads thin. Gravity would always pull matter into larger and larger structures given enough time. But in a dark, energy-dominated universe, structure growth effectively stops. The acceleration overwhelms gravity beyond certain scales. Existing structures remain bound, but no new, large-scale structures can form. The universe has already produced its last galaxy clusters. The largest gravitationally bound structures that will ever exist have already formed. From this epoch forward, the universe becomes less interesting, not more. Stars will continue forming for trillions of years as existing gas supplies are consumed, but no fundamentally new types of structures will emerge. Dark energy has frozen cosmic evolution at its current stage. The age of structure formation is ending. The age of endless expansion and increasing emptiness has begun. This transition from growth to stagnation occurs over timescales so vast they are difficult to comprehend. But the transition is real and inevitable if dark energy remains constant. The universe will not remain in its current state indefinitely. Change is coming. Not sudden change, not dramatic change, but inexorable change driven by acceleration that will transform the cosmos from a place of ongoing creation into a place of gradual decay. Understanding this future requires understanding the instruments and methods astronomers use to probe dark energy's properties across cosmic history, techniques that have reached extraordinary precision over the past 2 decades. The instruments used to measure dark energy represent some of the most sophisticated technological achievements in human history. These are not simple telescopes pointed at the SS pointed at the sky. These are precision machines designed to detect photons that have traveled billions of years through expanding space, measuring their properties with accuracies of a few % or better. Every component must work flawlessly. Mirrors must be polished to within billionths of a meter of perfect shape. Detectors must register individual photons with near-perfect efficiency. Electronics must amplify signals without adding noise. Software must process terabytes of data, correcting for atmospheric distortion, instrumental effects, and cosmic ray hits. The entire system, from primary mirror to final analyzed image, must maintain calibration over years of observations. This level of precision was unimaginable when dark energy was discovered in 1998. It has become routine in modern cosmology. The Hubble Space Telescope revolutionized dark energy measurements not through size, but through location and stability. Launched April 24, 1990, aboard Space Shuttle Discovery, Hubble's 2.4-meter mirror is modest compared to ground-based telescopes that now exceed 8 meters in diameter. But Hubble orbits above Earth's atmosphere at an altitude of roughly 540 kilometers, above the turbulence that blurs ground-based images. This allows Hubble to achieve diffraction-limited resolution, meaning its images are as sharp as the wave nature of light allows. More importantly, Hubble's orbit provides stable conditions. Temperature variations are small. Gravity's pull remains constant. Instrument calibration does not drift as weather systems pass overhead. These factors allow Hubble to measure the brightness of distant objects with systematic uncertainties below 2%, a remarkable achievement that took decades of careful engineering and operations to perfect. Hubble's observations of Cepheid variables in distant galaxies required pushing the telescope to its limits. Cepheids are bright stars, but in galaxies tens of millions of light-years away, they appear incredibly faint. Hubble's Advanced Camera for Surveys and Wide Field Camera 3 captured images of these galaxies repeatedly over weeks or months, watching individual stars brighten and dim. The images contained thousands of stars crowded together, each appearing as a tiny point of light, barely distinguishable from its neighbors. Sophisticated software analyzed these images, identifying which stars varied in brightness and measuring their pulsation periods. The periods ranged from a few days to several weeks. Longer period Cepheids are intrinsically brighter, following the period luminosity relationship discovered by Henrietta Leavitt. By measuring the apparent brightness and applying this relationship, astronomers determined distances accurate to roughly 5%. Hubble observed Cepheids in over 40 galaxies, building a precise calibration of the cosmic distance scale that anchored all subsequent supernova measurements. Ground-based telescopes compensated for atmospheric blurring through adaptive optics and by building on remote mountaintops where the atmosphere is thin and stable. The twin Keck telescopes in Hawaii, each with a 10-meter primary mirror composed of 36 hexagonal segments, began operations in 1993 and 1996. The Very Large Telescope in Chile, consisting of four 8.2-meter telescopes that can observe independently or combine their light, achieved first light in 1998. These facilities could observe much fainter objects than Hubble over wider areas of sky. They became crucial for discovering and following supernovae at high redshifts, where light from the explosions has been traveling for more than half the age of the universe. The telescopes observed the same patches of sky repeatedly, typically every few weeks, searching for new points of light that appeared suddenly and then faded over months. Computer algorithms compared each new image to previous observations, flagging potential supernovae for follow-up spectroscopy to confirm their type and measure their redshift. Spectroscopy extracts far more information than simple imaging. When a supernova's light passes through a prism or diffraction grating, it spreads into a spectrum showing how much light the object emits at each wavelength. This spectrum contains absorption and emission features produced by atoms in the supernova's outer layers. Silicon, oxygen, and other elements absorb specific wavelengths, creating dark lines in the spectrum. The pattern of these lines identifies the supernova type. Type Ia supernova show strong silicon absorption near 6,150 angstroms in their rest frame. But the expansion of space stretches all wavelengths by the same factor, redshifting the entire spectrum. A silicon line at 6,150 angstroms in a galaxy at redshift 0.5 appears at 9,225 angstroms when observed from Earth. Measuring this shift and dividing by the rest wavelength gives the redshift directly. Redshift then converts to distance through cosmological models that account for how space has expanded over the light's travel time. The characteristic scales that emerge from these measurements reveal dark energy's influence across billions of years of cosmic history. Supernovae at redshift 1, corresponding to light travel times of roughly 8 billion years, show measurable dimming compared to expectations from a decelerating universe. The effect amounts to about 0.3 magnitudes, where 1 magnitude represents a factor of 2.5 in brightness. This might sound small, but it accumulates over cosmic distances. A supernova that should appear at magnitude 24.0 appears at magnitude 24.3, dimmer by 30%. This systematic offset across dozens of supernovae at similar redshifts cannot be explained by random scatter or instrumental error. It represents genuine cosmic acceleration. At even higher redshifts approaching redshift 2, supernovae become too faint for current facilities to measure with sufficient precision, limiting how far back in time the supernova method can probe. Independent confirmation came from entirely different observational approaches that probe dark energy through its effects on cosmic structure rather than cosmic distances. The clustering of galaxies encodes information about how matter has been distributed by the combined effects of gravity and cosmic expansion. In the early universe, tiny density fluctuations, regions slightly denser or less dense than average, grew under gravity's influence into the galaxies and galaxy clusters we see today. But the growth rate depends on how fast space expands. Faster expansion means matter has less time to clump before being pulled apart by expansion. Dark energy accelerates expansion, suppressing structure growth. By measuring how strongly galaxies cluster at different distances, corresponding to different epochs in cosmic history, astronomers trace how structure growth has evolved and infer dark energy's influence. The Sloan Digital Sky Survey revolutionized galaxy clustering studies through systematic observations covering enormous volumes of space. Operating from Apache Point Observatory in New Mexico, The survey used a dedicated 2.5-meter telescope equipped with a wide field camera and sophisticated spectrographs. Between 2000 and 2008, the survey mapped over 900,000 galaxies across 8,000 square degrees, more than 1/5 of the entire sky. Follow-up surveys extended the observations to even larger samples. The BOSS survey, the Baryon Oscillations Spectroscopic Survey, observed over 1.5 million galaxies between 2009 and 2014. The eBOSS survey, extended BOSS, added nearly 800,000 more galaxies and over 200,000 quasars through 2020. Each spectrum measured the galaxy's redshift, allowing astronomers to map the three-dimensional distribution of structure across billions of light-years. These maps revealed a striking pattern. Galaxies are not distributed randomly, but cluster into filaments and sheets separated by enormous voids. The filaments span hundreds of millions of light-years, forming a cosmic web that traces the underlying dark matter distribution. Within this web, a subtle feature appears at a characteristic scale of roughly 490 million light-years. This is the Baryon Acoustic Oscillation Scale, imprinted when sound waves propagated through the hot plasma of the early universe. Before atoms formed photons and baryons, the ordinary matter particles were coupled together by electromagnetic interactions. Pressure waves rippled through this fluid, similar to sound waves in air but at speeds approaching half the speed of light. When the universe cooled enough for neutral atoms to form, photons decoupled from matter, and the pressure support vanished. The waves froze at their maximum extent, leaving a preferred separation scale between overdense regions. This scale has been stretched by cosmic expansion, growing from its initial value of about 450,000 light-years to nearly 500 million light-years today. By measuring this scale at different redshifts, astronomers track how space has expanded and detect dark energy's effect. The precision of these measurements reached remarkable levels through careful control of systematic effects. Galaxy clustering measurements can be contaminated by observational biases. Regions of sky obscured by dust in our galaxy contain fewer observed galaxies, not because they are truly underdense, but because the dust blocks light. Variations in observing conditions affect how faint galaxies can be detected, introducing artificial clustering patterns. The survey design and data analysis methods corrected for these effects through rigorous statistical techniques. Random sky positions were generated to represent uniform density, then weighted to match observing conditions at each location. Comparing real galaxy positions to these random samples isolated genuine clustering from observational artifacts. The final measurements determined the Baryon Acoustic Oscillation Scale to better than 1% precision, providing a standard ruler that constrained dark energy's properties independently of supernova observations. Gravitational lensing added yet another independent technique. Einstein's general relativity predicts that mass curves space-time, bending the paths of light rays passing nearby. This effect, called gravitational lensing, is not subtle. Galaxy clusters contain enough mass to visibly distort background galaxies into arcs and multiple images. But even in regions without massive clusters, the accumulated effect of all structure along the line of sight produces weak gravitational lensing, subtle distortions that stretch galaxy images by typically a few percent. These distortions are too small to detect in individual galaxies, but statistical analysis of millions of galaxies reveals the lensing signal. The strength of lensing depends on how much structure lies between us and distant galaxies, which depends on how structure has grown over cosmic time, which depends on dark energy. Measuring weak lensing across large areas of sky thus probes dark energy through entirely different physics than supernova or baryon acoustic oscillations. The Dark Energy Survey, operating from Cerro Tololo Inter-American Observatory in Chile, pioneered precision weak lensing measurements. The survey used a 570-megapixel camera, one of the most powerful astronomical cameras ever built, mounted on the 4-meter Blanco telescope. Between 2013 and 2019, the survey imaged 300 million galaxies across 5,000 square degrees of the southern sky. Each galaxy image was carefully measured to determine its shape, quantifying any distortion from gravitational lensing. The measurements required exquisite control of instrumental effects. Telescope optics introduced distortions that must be separated from genuine lensing. Atmospheric turbulence blurs images differently at different times. The camera's detectors have subtle variations in sensitivity across their surfaces. Correcting for all these effects demanded years of effort by dedicated teams of scientists and engineers. The survey also measured how galaxy clustering and weak lensing correlate. Regions with more galaxies should also show stronger lensing because both trace the same underlying matter distribution. But the correlation strength depends on how dark energy has affected structure growth. If dark energy suppressed growth, the correlation is weaker than it would be in a matter-dominated universe. The Dark Energy Survey measured this correlation across different distance ranges, probing dark energy's influence at different cosmic times. The results, published in detailed papers between 2017 and 2022, agreed with supernova and baryon acoustic oscillation measurements. All three independent techniques indicated dark energy makes up 68% of the universe and behaves like a cosmological constant to within measurement precision of a few percent. Recent technological advances promise even greater precision. The Dark Energy Spectroscopic Instrument, DESI, mounted on the 4-meter Mayol telescope in Arizona, began observations in 2021. DESI can simultaneously measure spectra for 5,000 galaxies using robotic fiber positioners that automatically move optical fibers to target positions. In a single night, DESI observes tens of thousands of objects. The 5-year survey aims to measure spectra for 40 million galaxies and quasars, mapping the universe in 3 dimensions with unprecedented detail. Early results, released in 2024, confirmed and extended previous measurements, determining the baryon acoustic oscillation scale and structure growth rate to sub-percent precision. The Vera C. Rubin Observatory, under construction in Chile and expected to begin operations in 2025, will survey the entire visible sky every few nights, using an 8.4-meter telescope and a 3.2 gigapixel camera. The survey, called the Legacy Survey of Space and Time, will image roughly 20 billion galaxies over 10 years. This enormous dataset will measure weak gravitational lensing across the full sky, detect thousands of supernovae at high redshifts, and trace structure growth with statistical precision far exceeding current surveys. Combined with space-based observations, these measurements will determine dark energy's equation of state to better than 1% and detect any evolution over cosmic time. The European Space Agency's Euclid mission, launched July 1, 2023, observes the universe from an orbit 1.5 million kilometers from Earth. Euclid's 1.2-meter telescope feeds 2 instruments, a visible camera and a near-infrared spectrometer. The mission will image 2 billion galaxies across 15,000 square degrees, measuring their shapes for weak lensing studies and their redshifts for clustering analysis. Operating above Earth's atmosphere provides stable conditions ideal for precision measurements. NASA's Nancy Grace Roman Space Telescope, scheduled for launch no earlier than 2027, will carry a 2.4-meter telescope, the same size as Hubble, but with a field of view 100 times larger. Roman will conduct deep surveys covering thousands of square degrees, discovering thousands of high redshift supernovae and measuring weak lensing over vast areas. Together, these missions will measure dark energy's properties with precision sufficient to detect deviations of 1% or less from a cosmological constant. The progression from early crude measurements to modern precision cosmology spans barely 3 decades but represents an extraordinary achievement. In 1998, dark energy was discovered through a few dozen supernovae, with distance uncertainties of 10 to 20%. Today, thousands of supernovae, millions of galaxies, and detailed maps of cosmic structure all point to the same conclusion, with uncertainties below a few percent. Independent techniques using different physics all agree. The measurements are robust. Dark energy is real. Its properties are constrained. Yet its fundamental nature remains mysterious. We measure its effects with extraordinary precision without understanding what causes those effects. This makes the study of dark energy both triumphant and humbling, showcasing our observational capabilities while exposing the limits of our theoretical understanding. The specific examples that emerge from these observations reveal dark energy's influence across the cosmos, from individual supernova explosions to the largest structures in the universe, each telling part of the larger story of cosmic acceleration. Individual supernovae that revealed cosmic acceleration tell stories of precision measurement and careful analysis. Supernova 1997 Apple, detected on March 24, 1997 by the High Z Supernova Search Team, exemplifies the challenges and triumphs of distant supernova observations. The explosion occurred in a galaxy at redshift 0.83, meaning its light traveled for roughly 7 billion years before reaching Earth. At peak brightness, the supernova appeared at magnitude 24, roughly 16 million times fainter than the faintest stars visible to the naked eye. Multiple telescopes observed it over several months as it brightened to maximum light, then faded. Spectroscopy confirmed it as type Ia. Careful photometry measured its peak brightness in multiple wavelengths. The data were painstaking to collect. Each observation required hours of telescope time. Atmospheric turbulence limited image quality. Cosmic rays struck the detectors, creating spurious signals that had to be identified and removed. Yet the final light curve, the plot of brightness versus time, matched the expected shape for type Ia supernovae almost perfectly. The supernova appeared roughly 0.25 magnitudes dimmer than it would in a decelerating universe. This single object provided one data point in the discovery of acceleration. Supernova 1997. Charlie Kilo, found September 7, 1997, resided even farther away at redshift 0.97. Light from this explosion traveled 8.1 billion years through expanding space. At this distance, dark energy's cumulative effect becomes pronounced. The supernova appeared 0.3 magnitudes dimmer than predictions from a matter-dominated universe, corresponding to roughly 35% less brightness or about 15% greater distance. The measurement uncertainty was larger than for closer supernovae because the object was so faint, but the systematic offset was clear. Multiple supernovae at similar redshifts showed consistent dimming. This was not random scatter. This was a pattern indicating that space had expanded more than expected during the light's journey. The universe had accelerated. Comparing supernovae across different redshifts reveals how acceleration has evolved. At redshift 0.1, corresponding to look-back times around 1.3 billion years, supernovae appear at their expected brightnesses within measurement errors. Dark energy's effect is too small to detect over such short timescales and distances. At redshift 0.3, roughly 3.5 billion years ago, a subtle dimming appears, about 0.1 magnitudes. By redshift 0.5, 5 billion years ago, the dimming reaches 0.2 magnitudes. At redshift 1, 8 billion years ago, it exceeds 0.3 magnitudes. This progression traces the transition from deceleration to acceleration. In the early universe, matter dominated and gravity slowed the expansion. Supernovae at the highest redshifts, beyond redshift 1, actually appear brighter than they would in a universe that was always accelerating, because expansion was slowing when their light began its journey. The brightness versus redshift relationship curves in a characteristic way that uniquely indicates a transition from deceleration to acceleration, roughly 5 billion years ago. What makes type Ia supernovae uniquely suited for these measurements is their standardizability combined with their immense brightness. Peak luminosity reaches roughly 5 billion times the Sun's brightness, making them visible across most of the observable universe. But they are not perfect standard candles. Intrinsic variations exist. Some type Ia supernovae are intrinsically brighter than others, with peak luminosities varying by factors of roughly 2. However, a remarkable relationship correlates peak brightness with how quickly the supernova fades after maximum light. Brighter supernovae fade more slowly. Dimmer supernovae fade more quickly. This width-luminosity relationship, discovered by Mark Phillips in 1993, allows astronomers to standardize the measurements. By observing how fast a supernova fades and applying a correction formula, the intrinsic peak brightness can be determined to within about 7%. This correction transforms type Ia supernovae from approximate standard candles into precision distance indicators. Recent discoveries have extended supernova measurements to even higher redshifts using space-based observations and gravitational lensing. In 2014, astronomers announced the detection of a supernova at redshift 1.91, designated SNUDS 10 Wilson. The explosion occurred when the universe was only 3.2 billion years old, less than a quarter of its current age. Light from this event traveled 10.5 billion years to reach Earth. The supernova was discovered by the Hubble Space Telescope during deep observations of a small patch of sky called the ultra-deep field. At such extreme distances, even type Ia supernovae are incredibly faint, requiring the most sensitive instruments and longest exposures. The measured brightness confirmed that the universe was decelerating at this early epoch, as expected from theory. This measurement, combined with those at intermediate redshifts showing acceleration and those at low redshifts showing continued acceleration, traces the complete history of cosmic expansion over more than 10 billion years. Gravitationally lensed supernovae provide an extraordinary opportunity to study dark energy through an entirely different phenomenon. When a massive galaxy cluster lies between Earth and a distant supernova, the cluster's gravity bends and magnifies the supernova's light, making it appear brighter than it would otherwise. In rare cases, the lensing produces multiple images of the same supernova, visible at different locations around the lensing cluster. The light paths to each image have different lengths, so variations in the supernova's brightness appear in the images at different times. In November 2014, astronomers discovered the first multiply-imaged supernova, named Refsdal, after Norwegian astronomer Sture Refsdal, who predicted this phenomenon in 1964. The supernova appeared in 4 images arranged in a cross pattern around a galaxy within the cluster Max J 114 9.5 plus 2 223, located at redshift 0.54. Detailed models of the cluster's mass distribution predicted that a fifth image would appear roughly 1 year later at a different location. The prediction was confirmed in December 2015, when the fifth image appeared exactly as calculated. The time delays between the images and their relative brightnesses depend on the cluster's mass distribution and the geometry of space, both of which are affected by dark energy. Future discoveries of more lensed supernovae will provide independent constraints on dark energy's properties. Similar phenomena appear in the behavior of galaxy clusters themselves, the largest gravitationally bound structures in the universe. Clusters contain hundreds or thousands of galaxies, along with vast quantities of hot gas and dark matter, with total masses reaching 1,000,000,000,000 times the Sun's mass. The abundance of clusters at different distances traces how structure has grown over cosmic time. In a universe where gravity dominates, clusters form more readily and grow to larger masses. In a universe where dark energy accelerates expansion, cluster formation is suppressed. By counting how many clusters exist at different mass scales and different redshifts, cosmologists infer dark energy's influence on structure growth. The Coma cluster, one of the nearest rich clusters at a distance of about 320 million light-years, contains over 1,000 identified galaxies and has a mass of roughly 1,000 trillion solar masses. This cluster formed when the universe was perhaps half its current age, in an era when matter still dominated and gravity could efficiently pull vast amounts of material together. Observations of Coma and similar nearby clusters reveal that they stopped growing in mass several billion years ago. The universe's acceleration has reduced the rate at which clusters can accrete new material from their surroundings. Future clusters will be smaller on average than those that formed in the past. The most distant massive cluster known, XLSSC 006, was discovered in 2016 at redshift 2.07, corresponding to when the universe was only 3 billion years old. This cluster contains roughly 100 trillion solar masses, already approaching the mass of mature nearby clusters, despite having formed so early. Its existence challenges structure formation models. Dark energy was negligible at such early times, so gravity should have been able to form clusters efficiently. Yet producing a cluster this massive by redshift 2 requires the initial density fluctuations to have been quite large, near the upper range of what inflation theory predicts. XLSSC 006 sites at the boundary of what is theoretically expected. Finding many more such massive high redshift clusters would indicate problems with standard cosmology. Finding none would suggest XLSSC 006 is a rare statistical fluke. Current surveys have not yet found comparable clusters at similar or higher redshifts, suggesting it may indeed be unusually massive for its epoch. The statistical distribution of cosmic voids, vast underdense regions spanning hundreds of millions of light-years, also encodes information about dark energy. Voids form in regions where the initial density was slightly below average. While overdense regions collapsed into filaments and clusters, underdense regions expanded faster than the average expansion rate, becoming progressively more empty over time. The largest known void, the giant void in the constellation, Cairnes Venatici, spans roughly 1 billion light-years and contains far fewer galaxies than similar volumes elsewhere. This void and others like it affect the cosmic microwave background through the integrated Sachs-Wolf effect, mentioned earlier. Photons passing through voids gain energy as they fall into the void's gravitational potential, then lose energy climbing back out. In a static potential, these energy changes cancel. But if the potential evolves, growing deeper or shallower, a net energy change occurs. Dark energy causes void potentials to decay over time, so photons gain a net energy boost, making the cosmic microwave background appear slightly hotter in directions through voids. This correlation between void locations and cosmic microwave background temperature has been detected statistically in large surveys, providing independent evidence for dark energy's effects on cosmic structure. Unexplained aspects remain in the details of these observations. The Hubble tension, discussed in Part 5, represents the most significant discrepancy, but smaller anomalies also appear. The amplitude of matter clustering on scales of roughly 8 megaparsecs, about 26 million light-years, shows a slight tension between measurements from the cosmic microwave background and direct observations of structure in the nearby universe. The cosmic microwave background, interpreted through standard cosmological models, including dark energy as a cosmological constant, predicts slightly stronger clustering than observed. The discrepancy is roughly 2 to 3 sigma, significant enough to warrant attention, but not decisive. It could indicate systematic errors in observations, incomplete modeling of complex astrophysical processes, or hints of new physics. Resolving this requires more precise measurements and better theoretical understanding of how galaxies form and evolve within dark matter halos. Ongoing research programs attack these questions from multiple angles. The Hypersuprime CAM survey on the Subaru telescope in Hawaii is mapping 500 million galaxies to measure weak gravitational lensing and galaxy clustering with unprecedented precision. The Atacama Cosmology Telescope in Chile is measuring the cosmic microwave background at small angular scales, where secondary effects like the Sunyaev-Zeldovich effect, the distortion of background radiation by hot gas in galaxy clusters, become prominent. The Dark Energy Spectroscopic Instrument continues its 5-year campaign to map 40 million galaxies and quasars. The South Pole Telescope measures polarization patterns in the cosmic microwave background, searching for signatures of primordial gravitational waves from inflation and constraining the sum of neutrino masses, both of which affect structure formation and dark energy measurements. Space missions provide complementary observations free from atmospheric interference. The James Webb Space Telescope, operating at infrared wavelengths where dust extinction is minimal, observes the most distant galaxies and supernovae, probing cosmic history when the universe was less than 1 billion years old. These observations test whether structure formed as predicted by models, including dark energy. The Euclid mission systematically maps 2 billion galaxies, measuring their shapes and distances to trace dark energy's effects over the past 10 billion years. Future missions like the Nancy Grace Roman Space Telescope will discover tens of thousands of supernovae at high redshifts, measuring the transition from deceleration to acceleration with far greater precision than currently possible. Theoretical work complements observations by exploring alternative explanations and predictions. Modified gravity theories continue to be developed and tested. Researchers calculate what observable signatures would distinguish a cosmological constant from dynamical dark energy or from modifications to general relativity. They simulate universe evolution under different assumptions, producing synthetic observations that can be compared to real data. They analyze whether combinations of known physics, perhaps involving neutrinos or other particles with unusual properties, could mimic dark energy's effects. None of these alternatives has proven compelling enough to replace the standard model, but the investigations continue because the stakes are so high. Understanding whether dark energy is truly Einstein's cosmological constant or something more complex will revolutionize physics either way. The examples from individual supernovae to vast cosmic voids all point toward the same conclusion. Dark energy dominates cosmic evolution. Its effects appear across every scale from individual objects to the largest structures. The measurements are consistent across independent techniques, yet puzzles remain. The Hubble tension persists. Small discrepancies in clustering amplitude appear, and the fundamental question of why dark energy has the value it does, neither zero nor enormously larger, remains unanswered. These mysteries drive continued research, pushing observations to greater precision and inspiring new theoretical ideas. Understanding dark energy requires not just measuring its effects, but also confronting how our perspective shapes what we observe, how our location in space and time limits what we can know, and whether the universe we see represents all of reality or merely a biased sample. The measurements revealing dark energy's dominance carry an uncomfortable assumption that we rarely state explicitly. We assume that what we observe from Earth represents the universe as a whole. We assume that the patch of space we can see, roughly 93 billion light-years across, is typical of all space. We assume that the laws of physics operate the same way everywhere, that the expansion rate we measure locally applies universally, that dark energy has the same density in distant regions as it does here. These assumptions seem reasonable. They form the foundation of modern cosmology, but they are assumptions nonetheless, and the universe has no obligation to conform to our expectations of reasonableness. What if our corner of the cosmos is special? What if we live in a bubble, a region whose properties differ from the vast, unseen universe beyond our observational horizon? Such possibilities are not idle speculation. They represent serious challenges to interpreting what our measurements actually mean. Consider how perspective limits cosmic observations. We sit at a single point in space, watching light arrive from all directions. This light left distant sources millions or billions of years ago, carrying information about conditions at those times and places. But we see only backward light cones, the collection of all events whose light has had time to reach us. Events beyond our horizon, regions of space whose light has not yet arrived or never will arrive due to accelerating expansion, remain forever invisible. We reconstruct cosmic history from fossils, from ancient light, that tells us what the universe was like in the past, not what it is like now. A galaxy we observe at redshift 2 as it appeared 11 billion years ago exists somewhere in space at this moment, but we cannot see its current state. Its light showing that current state will not reach Earth for another 11 billion years, by which time the universe will have changed dramatically. This temporal limitation means we never observe the present universe except in our immediate neighborhood. The spatial limitation cuts even deeper. The observable universe represents a finite bubble within what may be infinite space. Beyond our horizon lies more universe, potentially infinite in extent, but we have no direct access to it. If conditions beyond the horizon differ from conditions within, we would not know. If dark energy has different density in those unreachable regions, our measurements would not reveal it. If the expansion rate varies from place to place, we would only measure the local value. This raises an unsettling question. Are our observations telling us about universal properties, or merely about the particular bubble of space we happen to inhabit? The question is not merely philosophical. It has concrete implications for interpreting measurements and determining what they reveal about fundamental physics. Local structure affects measurements in subtle but potentially important ways. We sit roughly 50,000 light-years from the center of the Milky Way galaxy, within a spiral arm containing relatively high stellar density. The Milky Way itself belongs to the local group, a small cluster containing perhaps 80 galaxies scattered across a region roughly 10 million light-years across. The local group, in turn, lies on the outskirts of the Virgo supercluster, a vast collection of galaxy clusters spanning roughly 110 million light-years. Our motion through space reflects the gravitational pull of all this nearby structure. The Milky Way and Andromeda approach each other at 110 kilometers per second. The local group moves toward the Virgo cluster at roughly 300 kilometers per second. The entire region participates in larger-scale flows toward more distant concentrations of mass. These local motions must be subtracted from observed galaxy velocities to determine the true expansion velocity caused by dark energy. Errors in estimating local motions introduce systematic uncertainties in expansion rate measurements. More concerning is the possibility that our local region has unusual average density. If we live in a void, a region with below average matter density, local expansion would proceed faster than in denser regions. Observations of nearby galaxies would indicate a higher expansion rate than the cosmic average. This could mimic the effects of dark energy. Some researchers proposed in the mid-2000s that the apparent acceleration might be explained by our residing in a void roughly 200 million light-years across, with roughly 30% lower density than average. In such a scenario, no dark energy would be needed. The apparent acceleration would be a local effect, an artifact of our special location. However, detailed observations rule out this possibility. Measurements of galaxy clustering and the cosmic microwave background indicate that our local region has density very close to the cosmic average. We do not live in a large, underdense bubble. The acceleration appears genuine and universal, yet subtler variations could still affect measurements. The universe is not perfectly smooth. Density fluctuates on all scales. Our location within these fluctuations could bias observations in ways that are difficult to quantify. Imagine trying to measure the average temperature of Earth by sitting in one city and observing distant weather patterns. Your local temperature affects your instruments. Your position on the planet limits which regions you can observe. Weather systems between you and distant locations distort your measurements. Determining the true global average requires accounting for all these effects, a challenging task, even with sophisticated modeling. Cosmological observations face analogous difficulties. Our position within cosmic structure affects what we measure. Material between us and distant sources distorts their light. Extracting universal properties from position, dependent observations requires careful analysis and modeling. The typicality question extends to our cosmic epoch as well as our location. We live roughly 13.8 billion years after the Big Bang, at a time when dark energy has just begun to dominate but structure formation has not yet ceased. Is this typical? Would most observers throughout cosmic history find themselves at similar epochs? Or is our timing special? The anthropic argument mentioned in Part 4 suggests observers necessarily emerge during a relatively brief window. Structure must form, stars must live and die, heavy elements must be produced, planets must cool, life must evolve. This requires several billion years at minimum, but it also requires that dark energy not dominate too early, otherwise structure formation would be suppressed. The anthropic window might span only a few billion years in a universe that exists for trillions. Most of cosmic time would be too early for life, before stars formed, or too late for life, after stars burned out and dark energy rendered space too diffuse for interesting structures. We necessarily observe the universe during the brief interval when observers can exist. This makes our epoch special in an anthropic sense, even if it is typical among all epochs when observers exist. This reasoning invokes the Copernican principle the idea that we do not occupy a privileged position in the universe. Nicholas Copernicus argued in the 16th century that Earth was not the center of the universe, but merely one planet among several orbiting the Sun. This demotion of human centrality became a recurring theme in astronomy. The Sun is not the center of the galaxy, but one ordinary star among billions. The Milky Way is not the center of the universe, but one ordinary galaxy among billions. Our location in space appears typical, not special. The Copernican principle extended to cosmic time suggests we should exist at a typical time in the history of observers, not at some extraordinarily special moment. If observers can exist over a span of billions of years, we should find ourselves somewhere in the middle of that span, not right at the beginning or end. Applying this reasoning to dark energy suggests that if acceleration began 5 billion years ago, and observers can exist for perhaps 10 billion years total, we might indeed be typical. We live several billion years after acceleration began, with several billion years remaining before conditions become too harsh for life. This matches anthropic expectations reasonably well. However, some cosmologists argue the Copernican principle may not apply to observers in an accelerating universe. If dark energy remains constant, the universe will expand forever, growing increasingly empty and dark. Most of the future consists of an unimaginably vast expanse of near-perfect vacuum, punctuated by isolated dead stars and black holes. Observers, if any exist, would be extraordinarily rare in this far future. Perhaps most observers throughout all of cosmic history live relatively close to the transition to acceleration, during the final era when structure formation is possible. In this view, our epoch might be typical among all observer epochs, even though it represents a tiny fraction of total cosmic time. The debate remains unresolved. Different assumptions about what constitutes a typical observer and how observers are distributed across space and time lead to different conclusions about whether our observations reveal special or typical conditions. These considerations become particularly relevant when interpreting small discrepancies in measurements. The Hubble tension, for instance, might indicate new physics, or it might reflect our incomplete understanding of local structure and how it affects observations. If our local region participates in peculiar bulk flows, systematic motions of material on scales of hundreds of millions of light-years, this could bias local expansion measurements. The cosmic microwave background, coming from the entire sky at extreme distance, would not be affected by these flows. This could explain why local and early universe measurements disagree. However, current observations of local structure do not indicate sufficiently large peculiar velocities to explain the tension fully. The bulk flows measured through galaxy surveys reach velocities of a few hundred kilometers per second, significant, but not enough to cause a 9% systematic error in the Hubble constant. The tension persists. Future surveys aim to address these ambiguities through observations that probe much larger volumes and more cosmic history. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will image the entire visible sky from Chile every few nights for 10 years, detecting changes in brightness across billions of objects. This time domain astronomy will discover thousands of supernovae at all distances, providing unprecedented statistics on cosmic acceleration. The survey will also measure weak gravitational lensing by mapping 20 billion galaxies, constraining how structure has grown under dark energy's influence. Critically, the survey will cover the full sky visible from its location, allowing systematic checks for variations in dark energy's effects with direction. If dark energy density or the expansion rate varies across the sky, this survey could detect it. The square kilometer array An enormous radio telescope under construction with facilities in South Africa and Australia will eventually have collecting area of 1 square kilometre, 50 times larger than the next biggest radio telescope. The array will map hydrogen gas throughout billions of galaxies, tracing matter distribution back to when the universe was less than half its current age. Hydrogen emits radiation at 21 centimeters wavelength in its rest frame, but cosmic expansion redshifts this radiation. By measuring the redshifted wavelength, astronomers determine each galaxy's distance, building three-dimensional maps of cosmic structure. The enormous sensitivity of the square-kilometre array will allow mapping even the faint diffuse hydrogen in cosmic voids, revealing dark energy's effects in underdense regions where previous surveys had insufficient data. Space missions extend these measurements beyond Earth's atmosphere. The Nancy Grace Roman Space Telescope will survey 2,000 square degrees to depths where galaxies appear roughly 100 million times fainter than the faintest stars visible to the naked eye. At these depths, distant galaxies at high redshifts become accessible. The mission will discover roughly 10,000 Type Ia supernovae over its planned surveys, including many at redshifts beyond 1 where the universe was decelerating. These measurements will precisely constrain the transition from deceleration to acceleration, testing whether dark energy truly behaves as a cosmological constant over cosmic history. Roman will also measure weak gravitational lensing across its survey area, providing an independent probe of structure growth. The combination of multiple measurement techniques from the same mission allows powerful consistency checks that help identify systematic errors. The universe serves as a natural laboratory for studying dark energy because we cannot reproduce cosmic conditions on Earth. No experiment in a terrestrial laboratory can create volumes large enough or timescales long enough to test how dark energy affects expansion over billions of light years and billions of years. We must observe the cosmos itself, extracting information from light that has traveled across a significant fraction of the observable universe. This makes cosmology fundamentally different from experimental physics. We cannot control the experiment. We cannot vary parameters and rerun trials. We get one universe to study observed from one location at one cosmic time. Every measurement represents a historical observation, information about the past encoded in ancient light. Interpreting these observations requires assuming that physical laws apply universally, that our theoretical models capture relevant physics, and that systematic biases can be identified and corrected. These assumptions seem well justified based on the consistency of multiple independent measurements, but they remain assumptions. The philosophical implications run deep. If our measurements reveal only properties of our local cosmic bubble, not universal properties, then our understanding of dark energy might be fundamentally limited. We would know that something accelerates expansion in our region, but we could not confidently extrapolate to the entire universe. If cosmic conditions vary beyond our horizon in ways we cannot detect, the universe might be far stranger than we imagine. Some regions might have different dark energy densities, different expansion rates, different fundamental constants. The observable universe would be just one sample drawn from a vast ensemble of possibilities. This connects to multiverse ideas in cosmology and string theory, where our universe is one bubble in an eternally inflating cosmos containing infinite variation. Such scenarios are scientially speculative but intellectually serious. They remind us that our observations, no matter how precise, can only constrain what happens within our observable horizon. Beyond that, we extrapolate based on principles like Copernican typicality, but we cannot be certain. What makes these questions more than philosophical musing is that they affect how we interpret measurements and what conclusions we draw about fundamental physics. The Hubble tension, small clustering anomalies, and other discrepancies might indicate we live in an atypical region, or they might indicate genuine new physics requiring modifications to dark energy or gravity. Distinguishing these possibilities requires measuring larger volumes to assess cosmic variance, observing to higher redshifts to probe earlier epochs, and achieving sufficient precision that systematic uncertainties become negligible compared to statistical errors. Current and future surveys push toward these goals, mapping billions of galaxies across most of the observable universe, measuring cosmic expansion and structure growth to percent-level precision or better. As observational cosmology approaches its fundamental limits set by the finite age and size of the observable universe, we will know how typical or special our observations truly are. The long-term implications extend to the ultimate fate of everything, to the future evolution of cosmic structure, to the survival of complexity and information in an accelerating universe, and to the profound question of whether existence itself has meaning in a cosmos that may expand forever into increasingly perfect emptiness. The future stretches out in timescales that dwarf all of human history. 13.8 billion years have passed since the Big Bang. Perhaps 100 billion years remain before the last ordinary stars form from the last reserves of gas in the last galaxies capable of star formation. After that, the universe enters its long twilight, a period lasting trillions of years, where existing stars gradually burn out, one by one, never to be replaced. Red dwarf stars, the smallest and longest-lived, will continue fusing hydrogen for up to 10 trillion years. When the last red dwarf finally exhausts its fuel, perhaps 12 trillion years from now, no more light will be produced by ordinary stellar fusion. The universe will be dark except for the occasional brief flare as dead stars collide or as matter spirals into black holes. This is not the end, merely the end of the beginning. The universe will continue existing for timescales that make trillions of years seem like brief moments. Dark energy ensures this future is not just dark, but increasingly empty. As space accelerates outward, galaxies beyond our local gravitational neighborhood recede faster and faster. Eventually, they cross the cosmic horizon, the boundary beyond which objects recede faster than light. This does not violate relativity. Nothing moves through space faster than light, but space itself can expand at any rate, carrying distant objects with it. Once a galaxy crosses this horizon, its light can never reach us again. The observable universe shrinks. What we can see becomes limited to progressively smaller regions. In roughly 120 billion years, all galaxies currently visible beyond our local group will have crossed the horizon. An astronomer living in that distant future, looking out from the merged Milky Way Andromeda galaxy, would see only their own galaxy surrounded by empty blackness. The cosmic microwave background will have redshifted beyond detection. No external sources of light will be visible. Evidence for the Big Bang, for cosmic expansion, for the vast universe of galaxies will have vanished beyond the horizon. Future civilizations, if any exist, will have no way to discover these things through observation. The universe they can measure will consist of a single island of matter in an ocean of darkness. This observational horizon represents a fundamental limit on what can be known. Information beyond the horizon is causally disconnected. No signal, no influence, no measurement can bridge the gap. It is as if that distant matter no longer exists for practical purposes. Yet it does exist, continuing its own evolution in regions forever beyond our reach. The universe becomes partitioned into disconnected bubbles, each containing whatever matter was gravitationally bound before acceleration carried everything else away. Our bubble will contain the local group, perhaps several dozen galaxies with a combined mass of a few trillion suns. This is all that will remain observable. Everything else, the hundreds of billions of galaxies that fill our current night sky, will be gone, not destroyed, but removed beyond accessibility by the relentless stretching of space. The implications for life and intelligence are profound and troubling. Complexity requires energy flows, temperature gradients, regions where entropy can decrease locally by increasing elsewhere. Stars provide such gradients, producing light that drives chemistry and biology on orbiting planets. But stars are finite. Each one contains limited fuel. When that fuel is exhausted, the star dies. White dwarfs cool over trillions of years, radiating their residual heat into space until they become black dwarfs, cold, dark spheres that no longer emit measurable radiation. Neutron stars cool over similar timescales. Black holes persist far longer, but even they eventually evaporate through Hawking radiation, a quantum process where virtual particles at the event horizon become real, carrying away mass energy. A black hole with one solar mass evaporates in roughly 10 to the power of 67 years. A supermassive black hole with 1 billion solar masses takes 10 to the power of 99 years. These timescales are incomprehensible, but they are finite. Given enough time, every black hole will evaporate. After 10 to the power of 100 years, no significant structures will remain. The universe will consist of radiation, isolated electrons and positrons, and perhaps neutrinos, all separated by distances growing without limit. The existence of observers at other locations in space and time poses questions we cannot currently answer. Are we the only intelligent species in the observable universe? Almost certainly not, given the hundreds of billions of galaxies, each containing hundreds of billions of stars, many with planets in habitable zones. The sheer statistical probability suggests intelligence has arisen countless times across cosmic history. But where are they? Why have we detected no signals, no artifacts, no evidence of their existence? This is the Fermi paradox, named for physicist Enrico Fermi, who asked in 1950 where everyone was if the universe teems with life. Numerous explanations have been proposed. Perhaps intelligent civilizations destroy themselves before achieving interstellar communication. Perhaps the galaxy is colonized but deliberately avoiding contact with us. Perhaps we exist in a deliberately preserved nature reserve. Perhaps intelligence is extraordinarily rare, and we are alone. Dark energy adds another dimension to this question. Any civilization arising elsewhere faces the same ultimate constraints. Acceleration limits what volumes they can observe, what resources they can access, how long they can persist. The window during which intelligence can observe the wider universe and draw conclusions about cosmic history is finite, measured in hundreds of billions of years at most. Before this window opens, stars have not existed long enough to produce habitable planets. After this window closes, observational horizons shrink and energy sources dwindle. We exist within this window. So does any other intelligent species capable of understanding cosmology. The meta question about knowledge becomes particularly acute. What can observers know about the universe given their limited perspective? We have determined that dark energy dominates cosmic evolution, that the universe is accelerating, that this acceleration will continue indefinitely. But we inferred these conclusions from observations made during one brief epoch in one small region of space. Our entire scientific understanding rests on assumptions that we are typical, that physical laws apply universally, that our observations represent fundamental reality rather than local accidents. These assumptions appear well justified. Independent measurements agree. Multiple techniques converge on consistent conclusions. The theoretical framework of general relativity successfully predicts an enormous range of phenomena across all tested scales. Yet we cannot escape the fact that our knowledge is necessarily limited by our observational horizon and our position in cosmic history. We can never directly verify that dark energy has the same density in regions beyond our horizon. We can never travel to those regions to check. We can never observe the far future to confirm our predictions. We must extrapolate based on theories tested within accessible domains, hoping those theories remain valid beyond what we can measure. This epistemological limitation does not diminish the achievement of cosmology. We have gone from complete ignorance about the universe's composition and fate to detailed understanding supported by multiple independent lines of evidence. We have measured the age of the universe to within 1%. We have determined its composition to within a few percent. We have traced its expansion history across over 13 billion years. We have predicted its future evolution with confidence justified by theoretical consistency and observational confirmation. This represents extraordinary progress. But it also reminds us that science always operates at the boundary between knowledge and ignorance. Every answer raises new questions. Every measurement reveals new mysteries. The discovery of dark energy exemplifies this pattern. We set out to measure how much the expansion was slowing. We discovered instead that it was accelerating. This revelation answered one question but opened dozens more. What is dark energy? Why does it have the strength it does? Is it constant or evolving? Does general relativity require modification? The search for answers continues. The philosophical synthesis connects dark energy to broader questions about existence, purpose, and meaning, in a cosmos that appears indifferent to such concerns. The acceleration serves no purpose that we can discern. It does not optimize anything. It does not lead anywhere. It simply happens, a consequence of whatever physics governs the quantum vacuum, or the cosmological constant, or whatever dark energy truly is. The universe expands because the equations of general relativity, given particular initial conditions and energy content, predict expansion. The acceleration occurs because dark energy has negative pressure that generates repulsive gravity. There is no why in the teleological sense, no goal or intention. There is only how, the mechanistic unfolding of physical law acting on matter and energy distributed through space-time. Some find this realization liberating. The universe does not demand anything of us. We are free to create our own meanings and purposes. Others find it unsettling. We exist briefly in a cosmos that will eventually become hostile to all complexity. Our entire species, a momentary fluctuation in the long decay toward heat death. Yet here we are, alive and conscious, capable of measuring cosmic acceleration and pondering its implications. The universe has produced observers who can understand, at least partially, how it works. This seems remarkable regardless of whether we are common or rare among cosmic structures. The atoms in our bodies were forged in stars that exploded billions of years ago. The heavy elements essential for life emerged from nuclear fusion in stellar cores and from rapid neutron capture during supernova explosions. We are literally made of stardust, rearranged by chemistry and biology into forms capable of self-reflection. The fact that matter can organize itself into structures that comprehend their own origins and predict their future represents something profound, even if that future includes eventual dissolution. We exist during the brief window when observation is possible, when stars illuminate galaxies, when the cosmic microwave background remains detectable, when evidence for the Big Bang and cosmic acceleration can still be gathered. This timing may be necessary for intelligence to arise, but it also grants us access to understanding cosmic history. We are fortunate, in a sense, to live when and where we do. If this journey through dark energy and cosmic acceleration spoke to you, consider subscribing to this channel. There are more cosmic mysteries waiting to help you drift off into sleep enriched by understanding. Leave a like if you found peace in contemplating the vast scales of space and time. Share your thoughts in the comments about what aspect of dark energy intrigues you most. And good night, wherever you are in this vast, accelerating universe.